The age of the Earth is not just a set of numbers, but an entire epoch comparable to a majestic symphony where each note resonates over millions of years. If we imagine time as a vast hourglass, human life is but the tiniest grain of sand amidst an endless flow. The Earth began to take shape billions of years ago, and over this time it has witnessed numerous epochs, from the formation of the first oceans to the emergence of the earliest forms of life. The river of time, flowing through geological epochs, seems infinite, and within it, catastrophic events like the collision with a giant asteroid, which led to the extinction of the dinosaurs, are reflected. These giants dominated the planet for over 100 million years, and their disappearance paved the way for mammals, among whom, eventually, humans appeared. Human history is but a fleeting moment, like a flash of light in the boundless ocean of Earth's history. All great civilizations, from the Sumerians to the Roman Empire, existed for but a moment in comparison to the long history of our planet. If the entire history of Earth were compressed into 1 minute, human history would occupy no more than 1 second. We live in an era where science reveals new pages of this ancient book to us, and each discovery is like a new star shining on the horizon of our understanding. For example, paleontology, the study of fossilized remains, allows us to look back into the distant past and see how ecosystems that existed millions of years ago looked. Each fossilized skull, each petrified shell, tells a story of how life adapted to constant changes on the planet, whether it was changes in climate or tectonic movements. These processes occur slowly, but their consequences can be catastrophic. Atmospheric changes caused by volcanic activity can lead to global catastrophes that wipe out entire ecosystems. We, humans, are like a drop of water in this ocean of time, striving to leave a mark, but often forgetting that our lives are but a moment in the face of billions of years. Each day, when we wake up, we should remember that the Earth has already witnessed countless sunrises and sunsets, and each of these epochs has left its mark in the geological layers. It is important to realize that we are merely passengers on this gigantic cosmic ship, racing through space and time, over which we have no absolute control. Time is not just a linear sequence of events, but a complex network of interactions where each moment has significance. We must learn to appreciate each second, for it slips away into eternity like a grain of sand disappearing in the endless flow of the river of time. Scientific research shows that changes in climate and ecosystems are happening much faster than we can adapt to them. This underscores the importance of understanding our place in this complex and majestic structure. In the end, each of us is not just an individual, but a part of a gigantic mechanism that has been working for billions of years. Every action, every decision we take influences the future of our planet, and this emphasizes that we must be mindful in our actions. The Earth is not just a place where we live, but our home, which has its own history, its own rhythm, and its own mysteries. In this grand temporal scale, where billions of years merge into one, we must remember that each moment is an opportunity to create something meaningful. The current river of time carries us, but it is important to remember that we ourselves are part of this river, and each of our actions can leave a mark in its flow. At the very earliest stage of its existence, Earth was a searing, fiery sphere where surface temperatures reached colossal values exceeding thousands of degrees Celsius. This hellish sphere was covered in magma that boiled and churned like a giant pot on the verge of explosion. Volcanic eruptions occurred constantly, spewing vast amounts of lava, ash, and toxic gases into the atmosphere, creating a dull roar that echoed for millions of years. Complex processes of cooling and heating transformed the surface into something resembling a writhing skin, with hot magma pulsing beneath, and each new volcanic eruption sending clouds of superheated gas and dust obscuring the light from distant stars. The surface temperature was so high that all metals were in liquid form, flowing as rivers of molten iron and nickel through volcanic craters. The atmosphere at this time was opaque, filled with carbon dioxide and ammonia, making it deadly for any forms of life that might have existed in later epochs. This cocktail of toxic gases hid the fiery ocean from space, giving the illusion of complete emptiness, while catastrophic changes were taking place on the surface. Giant clouds of sulfur and water vapor obscured the sky, intensifying the sense of chaos and disorder. Periodically, powerful volcanic eruptions would hurl volcanic bombs reaching several meters in diameter that, upon impact, caused new explosions, destroying everything in their path. This world was a true laboratory of elemental forces where temperature and pressure could change at lightning speed, creating new minerals and rocks that would later form the basis for the continents. Such primitive chaos, like an endless dance, shaped Earth, preparing it for more tranquil and stable epochs. During this period, which lasted billions of years, the foundations of the planet were laid, with each drop of molten magma, each spark of eruption becoming part of the great game of nature. At this time, Earth was not just a planet, but a living entity, pulsating and breathing in rhythm with its catastrophic processes. From cosmic dust and debris scattered throughout the universe, the early Earth began to form. This process started about 4.5 billion years ago, when particles of cosmic material began to slowly attract each other under the influence of gravity. Initially, these were small dust particles and fragments, but as their mass increased, they formed larger objects such as planetesimals, protoplanets the size of modern asteroids. These planetesimals collided with each other, releasing enormous energy that turned solid matter into molten masses. Imagine vast fiery clouds heated to white-hot temperatures as two large objects collided, much like two massive stones striking each other, causing bursts of light and heat. As a result of these collisions, larger bodies formed, which in turn attracted more material, becoming increasingly massive. Under the influence of gravity, heavier elements like iron and nickel began to sink to the center of the forming world, creating a core that would become the foundation for the future planetary structure. Approximately 100 million years after the process began, Earth had gained enough mass to retain an atmosphere, although it was far from today's, comprising mainly water vapor, ammonia, and methane. Collisions with comets and asteroids continued, adding new elements and minerals to the young planet. It is worth noting that during this period, Earth was not the only object developing. Neighboring planets like Mars and Venus also formed from the same cosmic dust and debris, but with different outcomes leading to significant differences in their conditions of life. This formation process, like a grand spectacle, continued for millions of years, creating unique conditions for the further development of the planet. By the time Earth reached its final size, its surface was covered with oceans of molten magma, and its atmosphere was thick and inhospitable for life as we know it today. Each stage of this formation was crucial for the future existence of our planet, and it was in these conditions that the foundations for further evolution were laid. The first materials, such as silicate minerals, began to form, creating a solid shell that would later become the basis for continents. Over the following several 100 million years, this shell began to cool, paving the way for the appearance of the first forms of life. The process of Earth's differentiation occurred under conditions of a molten state, when the temperature on the planet's surface reached thousands of degrees Celsius. In this state, substances had high mobility, allowing them to move, interact, and arrange themselves according to their density. Heavier materials, such as iron and nickel, gradually sank to the planet's center, forming the core, while lighter substances, such as silicate minerals, rose to the surface. This can be compared to how oil finds its place on the surface of water, forming characteristic layers. Darker, denser liquids settle at the bottom, while lighter ones rise to the top, creating a clear separation. The process of differentiation was not just random, it was controlled and predictable, based on physical laws. As the outer layers of the planet cooled and solidified, the structure of the future Earth began to take on more stable forms. This process resulted in the formation of the mantle layer, which became the basis for tectonic plates, contributing to the formation of continents and oceans. It is worth noting that differentiation occurred over several million years, and its effects can still be seen today. For example, modern volcanoes like Kilauea on Hawaii continue to eject light materials that were formed as a result of complex processes that occurred during the early formation of Earth. This mechanism of separation by density not only determined the structure of the planet, but also laid the foundation for the emergence of the atmosphere and hydrosphere, which are necessary for life. In fact, it was the differentiation in the center of Earth that led to the formation of the iron core, which later became a key factor in the creation of the magnetic field of our planet. This field, in turn, protects Earth from solar radiation and allows life to exist in the form we know it. The formation of Earth's core was the result of a continuous process in which heavy metals, such as iron and nickel, gradually sank to the planet's center under the influence of gravity. This process began more than 4 billion years ago when Earth was still in a state of molten material. Gravity acted as an invisible magnet attracting denser elements. Iron, with a density of about 7.5 grams per cubic centimeter, and nickel, with a density of 8 grams per cubic centimeter, began to slowly move towards the center, leaving less dense elements on the surface. Over millions of years, during the process of differentiation, these heavy metals sank through layers of molten magma, forming the inner and outer parts of the core. The inner core, consisting mainly of iron and nickel, formed under immense pressure, reaching values of around 300,000 atmospheres at a depth of approximately 1,200 kilometers. This pressure is so great that it causes iron to exist in a solid state, despite the high temperatures, which exceed 6,000 degrees Celsius. The temperature is so high that under normal conditions iron would melt, but under the influence of pressure it remains solid. The outer core, located above, is in a liquid state, which is due to lower pressure values at which iron and nickel can maintain their fluidity. These processes occurred over millions of years, during which heavy elements passed through layers of molten material, encountering various underwater hot flows that also influenced their movement. The process of differentiation was uneven and depended on temperature, pressure, and the composition of materials, leading to the formation of complex structures within the Earth. Gradually, as the core grew larger, its influence on Earth's magnetic field began to manifest, creating a protective screen against solar radiation. By the end of this process, approximately 200 million years after the formation of Earth, the core became fully formed. The inner core reached a diameter of about 12,000 kilometers, and the outer core became a source of powerful convective currents that contributed to the dynamics of the magnetic field. This process of core formation became the basis for understanding many geophysical phenomena, such as earthquakes and volcanic activity, which are explained by the movement of materials in the mantle and their interaction with the core. The Earth's mantle is a massive layer between the core and the crust, occupying approximately 93% of our planet's volume. It extends to a depth of around 2,900 kilometers and is primarily composed of silicate minerals such as olivine and pyroxene, which become viscous and semi-liquid under high pressure and temperature. This consistency allows the mantle to move, creating slow but powerful currents that transport heat from deep layers of the Earth to the surface. The temperature in the mantle varies from approximately 1,000 to 4,000 degrees Celsius, resulting in a vast ocean of molten rock under immense pressure, reaching up to 400,000 atmospheres. These tectonic movements of the mantle, occurring at a rate of several centimeters per year, are the primary drivers of geological processes on the surface, such as earthquakes, volcanic eruptions, and mountain formation. For instance, Volcanoes like Kilimanjaro in Tanzania and Vesuvius in Italy arise due to magma formed in the mantle rising through the crust as a result of pressure and temperature. Each time the mantle moves, it affects the plate on which continents and oceans are located, as confirmed by the theory of plate tectonics proposed in the mid-20th century by scientists such as Alfred Wegener, who began to realize that continents are not stationary. The interaction of the mantle with the crust leads to the formation of new mountains, changes in topography, and even changes in the Earth's climate. The mantle also plays a crucial role in the carbon cycle, as carbon in the mantle can be released to the surface through volcanic activity, influencing the atmosphere and, consequently, the planet's climate system. An example of this process is the eruption of Mount St. Helens in the United States in 1980, which released a massive amount of volcanic gases, including carbon dioxide, into the atmosphere. Complex movements in the mantle, often taking the form of convective currents, are also responsible for the formation of oceanic ridges, such as the Mid-Atlantic Ridge, where new Earth's crust is formed. These processes serve as a constant reminder of how dynamic and changeable our planet is. Despite its hidden nature, the mantle remains one of the most important components of the Earth, determining many aspects of its geological activity. Approximately 4 billion years ago, a colossal collision with Theia occurred when young Earth encountered a protoplanet the size of Mars, known as Theia. This event was one of the most catastrophic in the history of our planet, leaving an indelible mark not only in geology but also in astronomy. At the moment of impact, the energy released was equivalent to several billion atomic bombs, resulting in a massive explosion that ejected a vast amount of material from the upper layers of Earth's mantle into space. Research indicates that the mass of the ejected material was about 1/3 the mass of the Moon. As a result of this catastrophic collision, a cloud of molten rocks and gases formed, which began to orbit Earth. This cloud consisted of fragments of Theia and Earth's crust, which were ejected due to the impact. Earth's gravity exerted its influence on this cloud, causing it to gradually coalesce and form the Moon. This process took approximately several tens of thousands of years, during which the Moon's mass decreased as some of the material fell back to Earth, while the rest continued to orbit the planet. The Moon formed in this way became not only Earth's satellite but also had a significant impact on its development, including the stabilization of its axis of rotation and the creation of tides. The collision with Theia altered the trajectory of Earth's development, making it more habitable due to the formation of the Moon, which created conditions for a stable climate. This moment in the planet's history can be compared to a birth, while the planet itself was experiencing a true catastrophe. The formation of the Moon occurred at a distance of about 30,000 kilometers from Earth, and since then it has been a constant companion, influencing many aspects of Earth's life. Scientific research, including the analysis of lunar samples collected during the Apollo missions, confirms that the chemical composition of the Moon is similar to that of Earth, indicating a common origin. The spatial and temporal connection of these events provides a unique context for understanding the evolution of our planet, and this collision was a key moment in the formation not only of the Moon, but also of the face of Earth as we know it today. The Moon, located approximately 380,000 kilometers from Earth, has become more than just a satellite. It is a crucial element in shaping the conditions necessary for life on our planet. These relationships began over 4 billion years ago when the Moon formed as a result of the collision between the proto-Earth and a Mars-sized object known as Theia. This event not only led to the formation of the Moon, but also had a profound impact on Earth's rotation and axial tilt, creating a stable climate. The presence of the Moon significantly influences the rhythms of tides and currents, affecting ocean ecosystems and the lives of organisms in coastal zones. Water masses respond to the Moon's gravitational pull, rising and falling to create a dynamic habitat for a wide range of marine life, from plankton to large mammals. This interaction shapes not only the physical conditions but also biological cycles, influencing the reproduction and migration of various species. The Moon also stabilizes Earth's axial tilt, ensuring the predictability of seasonal changes, which is crucial for the development of life. Without this stability, climate changes could be more abrupt and unpredictable, potentially hindering the evolution of complex life forms. Moreover, the Moon affects atmospheric processes, including the planet's rotation speed, which influences climate conditions. Throughout human history, the Moon has been a source of inspiration and scientific research, from ancient astronomers to contemporary space missions. On July 18, 1949, when the first lunar mission was launched, a new era in understanding the Moon's role in the Earth-Moon system began. Research indicates that the Moon may contain resources such as water in polar craters, which could be vital for future space colonies. This bond between Earth and the Moon, established billions of years ago, remains one of the oldest and most enduring in our solar system. The Moon, as an active participant in shaping conditions on Earth, continues to influence our world, underscoring its importance in the context of cosmic history. The gravitational pull of the Moon causes tides, which affect the oceans of Earth, causing them to move constantly. Tides occur twice a day when the Moon is above a certain part of the Earth, causing ocean waters to rise and form tidal waves that can reach several meters in height. On average, the height of the tide can vary from 1 to 2 meters, but in some places, such as the Bay of Fundy in Canada, tides can reach 9 meters. These fluctuations in water level shape coastal lines, creating unique ecosystems in tidal zones where marine life adapts to regular changes in its environment. Tidal zones, such as rocks and shallow areas, become homes for organisms like starfish, mollusks, and seaweed, which depend on the cyclic inflow of water for their existence. In ancient times, when the Moon was closer to Earth, its gravitational pull was much stronger, resulting in much more powerful tides. For example, about 1 billion years ago, when the Moon was only 300,000 kilometers away from Earth, tides could reach heights of up to 20 meters, crashing onto continents with immense force. These powerful tidal waves created vast shallow areas and flooded low-lying regions, contributing to the formation of new ecosystems and changes in landscapes. The Moon's influence on tides also plays a role in maritime navigation, as fishermen and sailors traditionally use knowledge of tides and currents to plan their journeys. Research shows that changes in water levels affect the behavior of marine organisms, including fish spawning and sea turtle migration, which depend on these cycles for reproduction. Therefore, the Moon is not just a silent observer in the night sky, but an active participant in the marine ecosystem, where its gravitational pull shapes not only water levels, but also life on Earth. Scientific studies show that even the slightest changes in the Moon's orbit can cause significant changes in tidal patterns, highlighting its inseparable connection to our planet. The Moon stabilizes the angle of Earth's axis, helping to maintain it within a range of 22 to 26 degrees. This massive presence of a satellite acts as an anchor, preventing chaotic oscillations of the planet's rotation axis. Scientists have calculated that without the Moon, the axis could have changed significantly, which would have affected the climate of Earth. For instance, during a period when Earth rotates around its axis at an angle of about 45 degrees, climatic conditions become extremely unstable, which could lead to rapid temperature changes and alterations in ecosystems. In the absence of lunar influence, such oscillations could occur with a periodicity of just a few thousand years, creating conditions in which complex forms of life could not have developed. This is evident from geological research data, which show that in the past, when the axis changed more rapidly, mass extinctions and abrupt climate changes occurred on Earth. For example, during the extinction of dinosaurs around 65 million years ago, the climate changed significantly, greatly impacting life on the planet. The Moon's gravity not only maintains the axis but also causes its gradual oscillations, which in turn contribute to the stability of climatic conditions. This allows ecosystems to adapt and develop, as well as promotes biodiversity. There are studies that show that if the Moon were lost, the Earth's climate system could become uncontrollable, leading to the creation of extreme conditions in which survival would be extremely difficult. For example, without the Moon, ecosystems could face abrupt temperature fluctuations that could lead to the disappearance of many species. A stable axis also influences the change of seasons, which is critically important for agriculture and ecology. Therefore, the Moon not only prevents climate catastrophes, but also creates conditions for the sustainable existence of life on Earth. Without its stabilizing influence, the development of complex forms of life would have become not only difficult, but practically impossible, which is confirmed by the research of climatologists and geologists. The cooling process of early Earth was truly remarkable and complex, akin to the cooling of molten metal or soup that gradually forms a thin crust on the surface. At the beginning of its existence, Earth was completely molten, consisting of magma and hot gases that boiled and bubbled like in a giant pot. In this state, the planet could have resembled a giant ball of lava with temperatures so high that any attempt at life would have been absurd. However, over time, due to natural processes, heat began to dissipate into space. This occurred through several mechanisms, including convection in the magma layer and the emission of heat as infrared waves. With each stage of cooling, a layer of solid crust formed on the planet's surface, much like the crust that forms on hot soup as it cools. This process was slow and uneven, and it laid the foundation for the formation of the first continents. In the early stages of cooling, when temperatures were still abnormally high, there were frequent volcanic activities, spewing hot rocks and gases into the atmosphere. These eruptions contributed to the formation of an atmosphere composed mainly of carbon dioxide, water vapor, and ammonia. Gradually, as the upper layer began to solidify, the first continents emerged. These continents were mountainous and volcanic, arising from tectonic activity. Various minerals and elements such as silicon and aluminum began to combine into more complex compounds, leading to the formation of the first mountain ranges. During the cooling and consolidation of the crust, water in the atmosphere began to condense and settle on the surface, forming the primary oceans. These oceans, rich in minerals, became the sites of the first chemical reactions, which later led to the emergence of life. Thus, the formation of a solid surface on Earth was a crucial stage in its history, setting the foundation for the planet's further development. The cooling of Earth not only resulted in the creation of a solid crust, but also established conditions for the presence of liquid water, which is critically important for life. At the boundary between the molten magma and the cooling crust, temperature and pressure began to create unique conditions that later became the basis for the formation of diverse ecosystems. As a result of this complex and prolonged process, Earth became a planet where life could develop, change, and evolve over millions of years. On the surface of the molten ocean of magma, which existed more than 4 billion years ago, the first solid sections of the Earth's crust began to form. These sections were thin, fragile crusts that formed as a result of rapid cooling of the magma. The temperature on the surface remained abnormally high, around 1200 degrees Celsius, which facilitated the formation of unstable but first islands of solid rock that floated on the surface of liquid rock. These islands were no more than thin layers consisting of basaltic rocks and were constantly subject to destruction. Internal forces of the planet, such as upwelling magma flows and volcanic activity, caused collisions between these sections, leading to their destruction and reformation. As a result of this dynamic process, entire lands appeared and disappeared on the surface of the magma ocean, as if playing an eternal game of tug-of-war. These first islands were far from the modern continents. They did not have a stable structure, and their shapes and sizes changed with each new lava eruption or strong earthquake. Many of these crusts did not survive to our time, but some of them, having survived, became the basis for future continents. During the period when the first crust was forming, volcanic processes also occurred. Magma rose to the surface, forming craters and lava flows. These craters, in turn, destroyed existing islands, creating new geological conditions. Thus, in some places, new crust sections were formed, while in others, their destruction occurred. This contradictory coexistence of stability and destruction reflected the youth of the Earth and its constant striving for change. Each new layer of crust formed during this period became a kind of witness to the chaos that reigned in those distant times. These processes led to the formation of the first continental platforms, but due to their instability, they could only exist for a limited time. As a result, after several million years, more stable and solid geological formations replaced these fragile crusts. However, it was these early experiments in crust formation that laid the foundations for the future continents and oceans that we know today. The first solid surfaces formed as a result of these processes were small in area, only a few thousand square kilometers, but they marked the beginning of a long and complex path of Earth's formation that continued for billions of years. The atmosphere of early Earth was a dense, opaque shroud of toxic gases that enveloped the planet, creating conditions entirely unsuitable for life as we know it today. This atmosphere was saturated with poisonous vapors rising from the scorching surface, where temperatures exceeded several hundred degrees Celsius. Volcanoes, actively erupting during this time, released significant volumes of carbon dioxide, sulfur dioxide, and methane into the air. These volcanic emissions primarily occurred between 4.5 to 3 billion years ago, when tectonic processes were particularly intense. Approximately 70% of the atmosphere consisted of carbon dioxide, which created a greenhouse effect, trapping heat and contributing to high surface temperatures. Additionally, sulfur dioxide, produced by the decomposition of organic matter and volcanic activity, filled the air with highly toxic compounds, making it lethal for modern life forms. In this atmosphere, there was no free oxygen, which was a critical factor hindering the development of aerobic organisms. The oxygen we take for granted did not exist in free form at that time, but was mainly bound in compounds such as water and iron oxides. Furthermore, the thick veil of gases prevented sunlight from reaching the surface, plunging the planet into eternal twilight. Studies show that the level of illumination was so low that photosynthesis as a process could not exist, ensuring the absence of life as we imagine it. As a result, the early state of Earth resembled a hellish environment, where high temperatures, toxic gases, and complete lack of light created a scene completely different from what we observe today. Therefore, when we talk about early Earth, it is important to remember that the conditions in which the first chemical reactions that led to the emergence of life took place were not just harsh, but extremely hostile. Approximately 2 billion years later, the atmosphere began to change gradually as cyanobacteria emerged, starting to produce oxygen and altering the composition of the atmosphere, creating conditions for the emergence of life on the planet. The process of degassing the planet was one of the key stages in the formation of its atmosphere. In the beginning of its history, Earth was a hot and turbulent place with active volcanic activity. Gases such as water vapor, carbon dioxide, ammonia, and methane were under high pressure, trapped in magma and rocks. Under the influence of enormous temperatures and pressures, these gases were gradually released. Volcanic eruptions played a central role in this process. Each eruption can be seen as a powerful exhalation of the planet, expelling portions of gases into the atmosphere. As a result of these eruptions, not only gases but also solid materials like ash and lava flows were released onto the surface. Volcanic vents formed by cracks in the crust served as a kind of ventilation, allowing Earth to breathe out accumulated gases. These processes continued for millions of years, creating conditions for the formation of the primary atmosphere, which then underwent changes as other elements and compounds began to emerge on the surface. With each new eruption, the composition of the atmosphere changed. Carbon dioxide, which was released in large quantities, became predominant, Over time, water vapor accumulated, condensing to form the first oceans. Simultaneously, other volatile components were released, also influencing the climate and conditions on the surface. This prolonged process of degassing led to the atmosphere of Earth acquiring a more complex composition, including oxygen, which became dominant due to the life activities of cyanobacteria. Volcanic activity, therefore, not only contributed to the formation of the atmosphere, but also played a significant role in shaping the climatic conditions on the planet. Over millions of years, these processes became the foundation for the formation of the gaseous envelope that protects Earth from cosmic radiation and retains the heat necessary for life. With each new volcano that breathed out gases, Earth gradually acquired the envelope we know today. As a result, the atmosphere of Earth consists of 21% oxygen and 78% nitrogen, making it unique among the planets in the solar system. As the Earth cooled, approximately billions of years after its formation, water vapor in the atmosphere began to condense. This process laid the foundation for the formation of the first oceans. When the surface temperature of the planet fell below 100 degrees Celsius, water vapor began to transform into droplets that fell onto the surface as torrential rains. These rains poured endlessly from the sky, creating images of catastrophic floods that lasted for thousands of years. Water released from the clouds filled low-lying areas and depressions, forming the first bodies of water. Scientists believe that this process began more than 4 billion years ago, when young Earth was still experiencing the aftermath of its active volcanic activity, which released vast amounts of water vapor into the atmosphere. With each new downpour that fell on the bare, uninhabited planet, the water level gradually rose, and small seas and lakes began to form. These bodies of water grew larger, filling all the available spaces between mountain ranges and plains. As a result, after several million years, the first oceans began to form, covering an increasingly larger portion of the Earth's surface. According to geologists, by 3 billion years ago, oceans already occupied about half of the planet, creating conditions favorable for the emergence of life. These primary oceans were rich in salts and minerals, a result of the leaching of substances from rocks and soil as the rains fell on the surface. The first oceans were not only the source of life but also a significant climate regulator, influencing weather patterns and the formation of atmospheric conditions. As water evaporated, it rose back into the atmosphere, creating cycles of precipitation that continued to shape the landscape of Earth. At this stage, when oceans already covered significant areas, processes began that ultimately led to the formation of continents. These continents, which later became home to ancient civilizations, were formed through tectonic processes where oceanic crust rose above the water level, creating land. Computer models show that by 2 billion years ago, oceans covered around 70% of the planet's surface. This means that due to the endless rains and gradual accumulation of water, Earth took on the form we know today. The appearance of the first oceans created an ideal environment for the emergence of life, as they provided the necessary conditions for chemical reactions that became the basis for the first organisms. These oceans became not just bodies of water, but also the cradle of life, which in the future would bring the first animals and plants to land. The first marine organisms, such as single-celled algae and bacteria, began to populate these waters, which in turn altered the chemical composition of the oceans and the atmosphere. As a result, by 1 billion years ago, the oceans became more oxygen-rich, leading to a true revolutionary change in the biosphere of the planet. The early ocean of Earth was vastly different from today's seas. Its waters were rich in minerals and organic compounds, leached from rocks and brought by meteorites that fell onto the planet. These meteorites contained crucial elements such as iron, nickel, magnesium, and silicon, which upon entering the ocean triggered complex chemical reactions. The temperature of this ocean could reach up to 100 degrees Celsius, while its acidity was at a level that would be lethal to modern organisms. The high temperature fostered the formation of various chemical compounds, creating conditions for endless reactions between minerals and organic substances. The ocean resembled a giant chemical laboratory where water, colored in vibrant hues from green to brown, underwent processes that ultimately led to the emergence of the first simple organisms. Unlike today's seas, which delight us with their transparent blue color and clean smell, the early ocean exuded a sharp and pungent aroma filled with sulfur and ammonia. The consistency of the water was thick and viscous, giving the impression of diving into a real chemical cocktail where each element played its role in the process of creating life. The abundance of metals gave the ocean a characteristic murky appearance, as if tiny particles were floating in it, reflecting light and creating blinding sparks. These conditions laid the foundation for the emergence of the first molecules of life, such as amino acids and nucleotides, which began to combine into more complex structures. All this occurred amidst constant volcanic eruptions, which added more minerals and gases to the ocean, creating a real storm of chemical reactions. As a result, the early ocean of Earth was not just a body of water, but the cradle of life, which in the future would populate the land and the sky. In the ancient oceans of Earth, there existed a unique primary broth, a complex mixture of various chemical substances that created ideal conditions for the emergence of life. This broth, in a sense, was a true nutritious soup, rich in building blocks that later evolved into all living organisms on the planet. The water that filled these oceans was abundant in carbon, nitrogen, and other elements necessary for the formation of the first molecules. The process was significantly influenced by energy sources such as lightning and ultraviolet radiation, which sustained constant chemical reactions. Lightning created conditions for the formation of new compounds by breaking molecules and causing them to combine into more complex structures. Ultraviolet radiation, penetrating the water, activated reactions that in turn contributed to the formation of organic molecules. Hydrothermal sources spewing hot water and minerals from the Earth's interior added not only heat, but also necessary minerals that could serve as catalysts for chemical reactions. These deep-sea sources could reach temperatures above 300 degrees Celsius, creating a unique environment where life could emerge in extreme conditions. This broth was not homogeneous. It contained diverse chemical compounds that interacted differently depending on the conditions, creating new molecules. Scientists believe that it was this nutritious soup that served as the cradle for the first simple organisms, which began to evolve, adapting to their surroundings. Complex molecules formed as a result of these reactions gradually evolved into more complex structures, such as cells, which later became the basis for all living beings. These processes occurred billions of years ago when Earth was just beginning to form as a planet suitable for life. The result was the creation of the first forms of life, which appeared around 3.5 billion years ago. The formation of amino acids and nucleotides in this primary broth became the foundation for the emergence of proteins and nucleic acids, essential for the growth and reproduction of organisms. It was this combination of factors and conditions in the ancient oceans that created a unique environment where life could not only emerge but also develop, forming the diversity we observe today. The study of these processes continues, revealing new horizons in understanding the origin of life on Earth and the mysteries it holds. Hydrothermal sources on the floor of ancient oceans represent unique underwater oases that form as a result of tectonic activity. These cracks in the ocean floor are outlets for hot, mineral-rich waters that rise from the Earth's interior to depths of more than 3,000 meters. The temperature of the water in these sources can reach over 300 degrees Celsius, creating ideal conditions for ecosystems based on chemical energy. One of the most famous examples of such sources are the black smokers, first discovered in 1983 off the coast of California on the Galapagos Ridge. These sources release black clouds of minerals such as sulfur and iron, which upon cooling form intricate mineral formations resembling volcanic cones. Around the sources there is a sharp gradient of temperature and concentration of various substances, creating a unique chemical environment. For example, near the sources the temperature can exceed 300 degrees, while just a few meters away the water temperature can drop to 0. This zone contrasts sharply with the cold, dark waters of the ocean, where the temperature may be only around 2 degrees. Research shows that complex ecosystems develop around hydrothermal sources, consisting of various types of bacteria that use chemical reactions to obtain energy. These bacteria form the basis of the food chain, providing nutrients for larger organisms such as worms and mollusks, which in turn attract predators. Scientists like Dr. Joanna Taylor have conducted research at ocean depths to understand how these unique ecosystems can provide insights into how life might have originated on Earth. In such extreme conditions, where sunlight does not penetrate, life continues to exist through chemosynthesis, challenging traditional notions of the necessary conditions for life. These sources can be considered a potential cradle of Earth's life, as it is here that the first microorganisms, which became the basis for further evolution, may have emerged. In 1999, a new form of life was discovered on the floor of the Pacific Ocean, known as hydrothermal worms, which could survive solely on the chemical substances released by the sources. Such findings support the hypothesis that life on Earth could have originated in conditions far removed from the familiar ecosystems we know. Today, the study of hydrothermal sources continues, opening new horizons in understanding not only the origin of life on our planet, but also the possibilities of life in extreme conditions on other planets. The formation of the first organic molecules in the ocean began with simple chemical compounds such as hydrogen, methane, ammonia, and water vapor, which recreated conditions similar to those that existed on early Earth. This process, known as abiogenic synthesis, became possible due to the high energy content caused by lightning and ultraviolet radiation. 14 billion years ago, when Earth was just forming, these gases dissolved in the primary oceans, creating a rich chemical environment. Experimental data from the Miller-Urey experiment conducted in 1953 demonstrate how simple molecules can combine to form more complex ones, such as amino acids, which are the building blocks of proteins. Under the influence of energy, molecules began to interact with each other, forming polymers consisting of long chains of atoms, significantly increasing their complexity. These polymers, due to their ability to self-organize, began to form more stable structures with specific functions. For example, RNA molecules, which can store and transmit genetic information, emerged as a result of these chemical reactions. Research shows that under conditions similar to those that existed on early Earth, organic molecules could form in special environments such as minerals or clay particles, which served as catalysts for these reactions. Over time, molecules began to interact more complexly, creating precursors to cells with elementary metabolic processes. These first steps from non-living matter to living organisms occurred due to the gradual complexity of chemical compounds, which is a key moment in the history of life on Earth. Scientific research indicates that this could have happened approximately 3.5 billion years ago, when the first single-celled organisms appeared, which already possessed the ability to self-reproduce and adapt, forming the basis for further evolutionary development of life. The study of self-replicating molecules opens up unique possibilities for understanding how life might have emerged on Earth. These molecules, which are complex chemical structures, have acquired the ability to create copies of themselves using available materials from their surroundings. In the process of self-replication, they act like seeds that, when placed in favorable conditions, begin to grow and develop. The principle of self-replication is based on the fact that molecules can interact with other chemical compounds, extracting the necessary elements to create copies of themselves. This occurs through specific chemical reactions where molecules, like builders, assemble their homes from surrounding resources. The conditions on early Earth, such as the presence of water, minerals, and organic compounds, created ideal conditions for the emergence of such molecules. Scientists believed that it was precisely the ability to self-replicate that allowed some molecules to spread across the planet, forming the first primitive forms of life. An example could be simple molecules that, by interacting with each other, formed more complex structures capable of further development. This ability to self-replicate marked a critical transition from chemical evolution, where chemical reactions occurred randomly, to biological evolution, where these reactions began to be governed by internal laws and mechanisms. Research shows that such molecules could have existed around 4 billion years ago, when conditions on Earth favored the formation of complex organic compounds. At that time, the diversity of self-replicating molecules could have led to the formation of the first cells, which became the basis for further evolution. Thus, self-replicating molecules can be considered the first settlers on the planet, which, once arising in a favorable environment, could adapt and evolve, creating increasingly complex and diverse forms of life. This became the foundation for the emergence of various biological processes that we observe today. A significant milestone in the study of self-replicating molecules was the discovery that some of them could not only copy themselves but also evolve, changing under the influence of their surroundings. This process of evolution in turn could have led to the appearance of new properties and functions, which later became the driving force for the development of life on Earth. The first self-replicating molecules became the basis for a complex biological system that, as we know, led to the formation of all living organisms. These molecules, like seeds that germinate in conditions conducive to life, created conditions for the formation of the first ecosystems. Models of molecular evolution show that self-replicating structures could form communities, interacting and exchanging genetic information. This exchange promoted the development of diversity, ultimately leading to the appearance of multicellular organisms and complex ecosystems. Such molecules, like the first grains sown in the soil of life, became the basis for all subsequent forms of life, from single-celled to multicellular organisms that inhabit our planet today. In the early stages of life's formation on Earth, molecules such as phospholipids began to gather into thin films, forming primitive cellular membranes. These molecules have a unique structure. One part is hydrophobic, disliking water, while the other is hydrophilic, attracting water. Thus, in an aqueous environment, lipids began to self-assemble, forming spheres that can be visualized as bubbles separating the internal contents from the external environment. These primitive membranes became the first line of defense for emerging life processes, providing a safe space for chemical reactions. The formation of these membranes was not static. They could grow, divide, and fuse, creating increasingly complex structures. For instance, when two bubbles fused, their contents could mix, increasing the diversity of chemical reactions within these structures. This was a critical step in evolution, as the appearance of membranes allowed for the concentration of chemical reactions in a confined space, significantly accelerating evolutionary processes. These membranes did not merely separate the insides from the external world, but also created conditions for the emergence of new properties, such as metabolism and replication. Such bubbles could reach diameters of around 10 micrometers, allowing them to interact with the surrounding environment, absorbing necessary molecules and repelling unwanted ones. As a result of these complex interactions, the first protocells emerged, capable of extracting energy from the surrounding environment, which became the foundation for further evolutionary processes. These structures became the predecessors of true cells and paved the way for the appearance of multicellular organisms. The appearance of cellular membranes was a turning point in evolution, as they allowed for the isolation and protection of biochemical processes, thereby facilitating the development of more complex forms of life. The first prokaryotic cells were single-celled organisms that appeared on Earth approximately 3.5 billion years ago and became the first forms of life on the planet. These microorganisms lacked a nucleus and complex internal structures, making them the simplest forms of life at that time. Prokaryotes, such as archaea and bacteria, ranged in size from 1 to 10 micrometers. Their cellular structure was extremely simplified. Genetic information was stored in a circular DNA molecule freely floating in the cytoplasm, not enclosed in a nucleus as in more complex eukaryotic cells. These cells could utilize various energy sources, including photosynthesis and chemosynthesis, allowing them to survive in conditions where oxygen in the atmosphere was extremely scarce. For example, cyanobacteria, which appeared later, began to produce oxygen during photosynthesis, which was a significant step in changing the Earth's atmosphere. Prokaryotes reproduced by division, a process known as binary fission, in which one cell divided into two identical daughter cells. This process was fast and efficient, enabling prokaryotes to quickly colonize various ecosystems, including hot springs, acidic lakes, and even deep-sea fissures. Their remarkable resilience allowed them to survive in extreme conditions such as high temperatures and high salt concentrations, making them some of the most adaptable organisms on the planet. Prokaryotes formed the basis for further life development, as they not only survived the conditions of early Earth, but also created conditions for the emergence of more complex multicellular organisms, including animals and plants. Large colonies of prokaryotes that formed in primordial oceans could reach sizes visible to the naked eye, as seen with the well-known stromatolites, rocky formations created by cyanobacteria. These ancient organisms demonstrated an incredible ability to survive and adapt, which became the foundation for further evolution of life on Earth. They did not just exist but actively participated in the planet's biochemical cycles, including the carbon and nitrogen cycles, enabling ecosystems to develop and become more complex. Stromatolites are one of the oldest and most fascinating evidence of life on Earth, representing layered structures formed by colonies of microorganisms, primarily cyanobacteria. These organisms, which existed billions of years ago, began to harness oxygen and photosynthesis, marking a pivotal moment in the evolution of life. Stromatolites form through a complex process where microscopic bacterial mats capture sedimentary particles from the surrounding environment, such as sand and clay. These mats, composed of millions of microorganisms, create layers that over time become compacted and mineralized, resulting in characteristic domes and columns. Over millions of years, stromatolites grow extremely slowly, adding new layers one by one, allowing us to observe the passage of time, much like the annual rings of trees. Each layer of a stromatolite can indicate various environmental conditions, such as salinity, temperature, and the presence of nutrients. For instance, changes in climate or ecosystem can cause stromatolites to alter their shape and structure, reflecting these changes in their layers, making them true chronicles of evolution. Some stromatolites can reach significant sizes, up to several meters in height, and their structure can contain various minerals like calcite and aragonite, indicating the diversity of chemical processes involved in their formation. These structures are not only unique in their nature, but also serve as important indicators of ancient life, helping scientists better understand how the biosphere on our planet evolved. Stromatolites, as the earliest builders on Earth, open a window into a world dominated by microorganisms. Studying stromatolites also helps us understand how ancient organisms could influence the Earth's atmosphere by releasing oxygen and thus contributing to the emergence of more complex forms of life. Knowledge of stromatolites is actively used in paleontology and geology, enabling researchers to reconstruct ancient ecosystems and their ecological conditions. These structures, despite their simplicity, are vital witnesses to biological evolution and climate change over billions of years. Stromatolites, like ancient books, preserve information about how life on Earth adapted and evolved in response to changing conditions. Shark Bay in Australia, located on the country's western coast, is home to unique stromatolites. colonies of cyanobacteria that form structures identical to those that existed billions of years ago. These living fossils represent not only scientific value but also a breathtaking sight. In the shallow waters of the bay with high salinity, the transparent water reveals rounded domes and columns formed by the oldest forms of life. Stromatolites here grow slowly, adding less than 1 millimeter per year, making them true witnesses to Earth's geological history. This bay, declared a UNESCO World Heritage Site in 2002, provides ideal conditions for stromatolite growth due to warm water and high salt concentration, allowing cyanobacteria to effectively photosynthesize. The stromatolites of Shark Bay are the result of centuries of mineral accumulation that adheres to living cells and forms layers, creating characteristic shapes. These structures are not only unique ecosystems but also important indicators of climate change and environmental conditions. Scientists like Dr. Carolyn West and her team from the Australian National University actively study these formations to understand how they have adapted to environmental changes over millions of years. Stromatolites help researchers look back into the distant past of our planet, as they have preserved information about ancient ecosystems and climatic conditions that existed when oxygen was just beginning to accumulate in the atmosphere. Therefore, stromatolites are not only living fossils, but also important sources of information about how life on Earth has evolved and adapted to changes. These formations remind us that life on our planet has a long and complex history, filled with changes, evolutions, and adaptations. The stromatolites of Shark Bay are not just geological formations, but ancient books that open before scientists' pages of history hidden at the bottom of the bay, where each drop of water can tell its story, reflecting billions of years of evolution. Photosynthesis is one of the most significant biochemical processes on Earth, which has become the foundation of life as we know it. It represents a revolutionary conversion of solar energy into chemical energy, enabling living organisms to capture sunlight and use it to create nutrients. This mechanism emerged around 3 billion years ago when simple organisms began to harness light as a source of energy. As a result, oxygen and organic compounds began to be released into the atmosphere, fundamentally altering its chemical composition. Scientists believe that it was due to photosynthesis that the level of oxygen in the atmosphere increased from less than 1% to 21%, paving the way for the emergence of more complex forms of life. In this process, sunlight is absorbed by pigments that capture light and convert it into chemical energy. This energy is then used to synthesize organic molecules from simple substances such as carbon dioxide and water. In essence, photosynthesis has become a powerful mechanism that allows living organisms, from single-celled organisms to massive trees, to harness solar energy and convert it into food. With each new step in evolution, photosynthesis has developed and become more complex, opening new horizons for life on Earth. This process has become the basis for the formation of ecosystems where various species interact with each other, creating complex food chains. It is important to note that photosynthesis not only supports life on the planet but also plays a crucial role in maintaining the climate by regulating the level of carbon dioxide in the atmosphere. It has also become the basis for agriculture and the food chain, providing nutrients to almost all living organisms. Research shows that photosynthetic organisms such as algae produce more than half of the oxygen we breathe. A striking example is phytoplankton, which, despite its microscopic size, significantly influences the composition of the atmosphere and oceans. This process, which has been occurring for billions of years, has not only transformed the planet, but has also become the key to the formation of the biosphere we know today. Photosynthesis is not just a chemical reaction, it is a fundamental process that links solar light with life on Earth. Cyanobacteria, or blue-green algae, were the first organisms on Earth to engage in photosynthesis, and their impact on the planet can be considered one of the most significant in history. These microorganisms, which appeared around 3.5 billion years ago, mastered the ability to use solar energy to synthesize organic compounds from carbon dioxide and water. They release oxygen as a byproduct, and this process laid the foundation for the formation of Earth's oxygen-rich atmosphere. In ancient geological epochs, cyanobacteria formed extensive colonies, coloring shallow waters in vivid blue and green hues, creating unique ecosystems. Colonies of cyanobacteria, such as stromatolites, are accumulations of layers that formed over millions of years due to the deposition of limestone. These structures can be found in modern seas, but their age can reach 3 billion years, making them some of the oldest fossils on the planet. The photosynthesis process carried out by cyanobacteria altered the chemical composition of the atmosphere, increasing the oxygen content from less than 1% to more than 21% over several hundred million years. This change led to what is known as the oxygen catastrophe, around 2.5 billion years ago, when oxygen began to accumulate in the atmosphere, paving the way for the development of aerobic organisms and complex life. Scientists such as Dr. Mary D.S. Johnson from the Institute of Ecology emphasized that cyanobacteria not only transformed the atmosphere, but also became the basis for the ecosystems we observe today, providing nutrients for many other forms of life. These tiny organisms, which reproduce by division, can form massive colonies in a wide range of conditions, from hot springs to cold bodies of water. Their ability to survive in extreme conditions makes cyanobacteria unique and vital for understanding the evolution of life on Earth. It is important to note that cyanobacteria continue to play a crucial role in modern ecosystems, participating in the carbon and nitrogen cycles. As a result of their activity on the planet, conditions were created that allow complex forms of life, including humans, to exist. Cyanobacteria, with their ability to photosynthesize, have become an integral part of the biosphere, and their influence has been felt over billions of years. According to research, cyanobacteria are responsible for approximately 30% of the oxygen we breathe today. The oxygen catastrophe was one of the most dramatic events in Earth's history, when the atmosphere and oceans underwent sharp changes due to the accumulation of oxygen produced by cyanobacteria. This process, which led to a significant increase in oxygen levels, posed a severe challenge for most organisms that had adapted to an anoxic environment. For them, oxygen became a toxic substance, similar to how carbon monoxide is toxic to us. Organisms of that time, such as anaerobic bacteria, lacked any adaptations to cope with this new chemical reality. They thrived in conditions where oxygen was practically non-existent, and their metabolism had adapted to this environment. Gradually, as cyanobacteria continued to produce oxygen, the concentration of this gas in the atmosphere reached critical levels. This paradox, an element essential for the survival of most modern organisms, became a deadly poison for those who lived billions of years ago. The process of oxygenating the atmosphere led to mass extinctions. Many species were unable to adapt to the new conditions and disappeared, paving the way for new forms of life that could use oxygen for metabolism. During this time, aerobic organisms evolved and learned to use oxygen to generate energy, contributing to the diversity of life on Earth. In this context, oxygen became not just a poison, but a catalyst for a new era on the planet. The oxygen we consider essential for breathing was once the cause of the demise of billions of organisms that inhabited Earth. The oxygen catastrophe illustrates how global ecological changes can fundamentally alter the biosphere, leading to rapid evolutionary leaps. This event laid the foundation for the emergence of complex multicellular organisms that subsequently populated the oceans and land. It is thanks to this transitional phase in Earth's history that we can observe the diversity of life that exists today. The oxygen catastrophe not only altered the composition of the atmosphere but also influenced climate conditions, creating a platform for the formation of ecosystems that we know today. For example, many plants, such as mosses and ferns, began to flourish in conditions of increased oxygen concentration, creating terrestrial ecosystems. The appearance of oxygen in the atmosphere also led to the formation of the ozone layer, which protected life on Earth from ultraviolet radiation. Ultimately, this dramatic shift in the chemistry of our planet opened new horizons for the evolution of life, making oxygen not only a necessary element but also a crucial factor in the development of ecosystems. Oxygen, which is now the basis for the existence of most modern forms of life, was once a poison for those who lived billions of years ago. During the oxygen catastrophe that occurred approximately 2.5 billion years ago, the oceans underwent significant changes that permanently altered their chemical composition. In ancient seas rich in dissolved iron, oxygen, which began to accumulate in the atmosphere, reacted with iron, leading to the formation of iron oxides. This oxidation process became a catalyst for massive changes in the oceanic ecosystem. Iron oxides formed as a result of this reaction precipitated onto the ocean floor as sediment, forming characteristic banded iron formations known as iron formations. These formations, consisting of red banded deposits, are a testament to this monumental period in Earth's history. They were formed through the gradual accumulation of sediments containing various iron compounds, and their typical red coloration indicates a high content of iron oxides, such as hematite. During the oxidation of iron, when iron dissolved in water was oxidized to oxides, the old greenish and grey hues of the oceans began to fade, giving way to the brighter and clearer blue colors we observe today. This transition was not only a visual change, but also an indicator of significant ecological changes, as the oxygen released by photosynthetic microorganisms altered the composition of ocean water and its ability to support life. The increase in oxygen also led to a greater diversity of marine life, as new organisms began to develop and adapt to the changing conditions. The banded iron formations we can see today in some geological formations are not only evidence of oxidation processes, but also important indicators of changes in the composition of the atmosphere and oceans that occurred during that period. These layers of sediment, formed over millions of years, serve as a valuable archive, allowing scientists to study climate changes and the evolution of life on Earth. It is interesting to note that in some places, such as Brazil and Australia, large deposits of these iron formations have been preserved, which have become important sources of iron for modern humanity, underscoring their significance not only for geological but also for economic processes. The discovery of oxygen in Earth's atmosphere was a true turning point in the evolution of life, and it's not just a metaphor. About 2.5 billion years ago, during the Great Oxygenation Event, the level of oxygen in the atmosphere rose sharply due to photosynthetic bacteria, known as cyanobacteria. These microorganisms, capable of converting sunlight into chemical energy, began to release oxygen as a byproduct. As a result, oxygen became available not only to simple single-celled organisms, but also to more complex forms of life. However, oxygen is not just a source of life, it is also a potential destroyer. Many organisms were unable to adapt to the new conditions and went extinct. But those that survived began to develop protective mechanisms. For example, some bacteria evolved enzymes such as catalase and peroxidase, which neutralize the toxicity of hydrogen peroxide formed during oxidation. Evolutionary adaptation to oxygen led to the development of aerobic respiration, significantly increasing the energy efficiency of organisms. Instead of simple decay or fermentation processes, eukaryotes began to use oxygen to produce ATP, the main source of energy in cells. This became the basis for the formation of more complex multicellular organisms. For instance, algae, which use oxygen for respiration, began to develop complex structures such as roots and leaves, which in turn opened the way for the colonization of land. Around 600 million years ago, the Cambrian explosion occurred, a burst of biodiversity when the first multicellular organisms, such as trilobites and sea lilies, appeared. This was a time when life on Earth began to thrive in new conditions, and oxygen became not just a component of the atmosphere, but a true catalyst for biological evolution. New forms of life, such as predatory species, began to develop the ability to move quickly, leading to the formation of complex ecosystems. As a result, adaptation to the oxygen-rich atmosphere paved the way for the emergence of highly organized animals, including the ancestors of vertebrates, which occurred around 500 million years ago. Adaptation to oxygen ensured not only survival but also the flourishing of species, which became the basis for the formation of the ecosystems we know today. This process demonstrated how changing conditions can lead to an incredible diversity of life forms. Oxygen became not just a necessary element for breathing, but also a crucial factor contributing to evolutionary changes that ultimately led to the appearance of humans and complex ecosystems. An eukaryotic cell is a more complex structure compared to prokaryotes, which are primitive cells without a nucleus. Eukaryotes emerged approximately 1 billion years ago and became the foundation for the development of multicellular organisms. These cells can be visualized as miniature cities where each part performs specialized functions, allowing the organism to adapt to various environmental conditions. Inside the eukaryotic cell, there is a nucleus, which is isolated from the rest of the cell and contains genetic material in the form of DNA. This is like the main office of the city, where all important instructions for functioning and development are stored. Surrounding the nucleus are various structures, each performing its role, such as in protein synthesis or energy production. This makes the cell more efficient and organized than its prokaryotic predecessors. The appearance of eukaryotes marked a revolutionary leap in the complexity of living systems, as they became the basis for the development of all higher forms of life, including plants, animals, and fungi. Eukaryotes have the ability to divide, allowing them to grow and develop into complex organisms. The system of management and distribution of functions within the eukaryotic cell allows the organism to respond to changes in the environment, which is a key factor in survival. The presence of specialized cellular structures, such as mitochondria, which produce energy, makes eukaryotes more adapted to various conditions. Unlike prokaryotes, eukaryotes can form multicellular organisms, opening new horizons for evolution. An example of this is algae, which, being single-celled eukaryotes, were able to organize into multicellular forms, becoming the basis for the appearance of plants. Eukaryotic cells can also form tissues and organs, significantly increasing their complexity and functionality. Their ability to perform specialized activities and interact with other cells leads to the creation of complex ecosystems where each cell performs its role, like a worker in a large production process. This interaction between cells also facilitates the exchange of genetic information, which is an important aspect of evolution. Eukaryotic cells can exchange genes through horizontal gene transfer mechanisms, increasing their genetic diversity and adaptive capabilities. An example of this is fungi, which can exchange genes with plants and bacteria, contributing to their survival in various ecosystems. The diversity of forms and functions of eukaryotic cells plays a key role in ecosystems, allowing the creation of complex food chains and networks of interactions between organisms. With the appearance of eukaryotic cells on Earth, a new era in biology began, opening the way to the appearance of the diversity of life that we observe today. Eukaryotes became the basis for the emergence of complex organisms, including humans, and their evolution continues to this day. The eukaryotic cell is not just a building block of life, but also a testament to how evolution can lead to an incredible diversity of life forms. The theory of endosymbiosis explains the origin of mitochondria, presenting an intriguing picture of how ancient bacteria capable of aerobic respiration became an integral part of larger cells. Around 1.5 billion years ago on Earth, eukaryotes emerged, and it was during this period that a fascinating encounter between two organisms likely occurred. A primitive eukaryotic cell engulfed an aerobic bacterium that could effectively use oxygen, but instead of digesting it, the cell decided to host it within itself. This process marked the beginning of symbiotic relationships where both parties benefited. The bacterium provided the cell with energy, while the cell offered protection and necessary nutrients. This mutually beneficial union laid the foundation for the creation of mitochondria, which today can be referred to as energy stations of cells. Notably, mitochondria retained their own DNA, which differs significantly from the nuclear DNA of eukaryotes. This DNA contains genes essential for the synthesis of proteins specific to mitochondria and indicates their bacterial origin. Mitochondria have a double membrane, confirming their complex evolutionary history. The inner membrane forms folds called cristae, which increase the surface area for biochemical reactions such as oxidative phosphorylation. This process, in turn, allows cells to produce adenosine triphosphate, ATP, a universal energy molecule necessary for all life processes. Research shows that mitochondria possess unique division mechanisms reminiscent of bacterial division, further confirming their symbiotic past. This remarkable combination of two different organisms led to the formation of complex multicellular life forms, including humans. Moreover, mitochondria participate not only in energy production, but also in regulating cellular metabolism, controlling apoptosis, and even maintaining homeostasis. Thus, the symbiosis between the eukaryotic cell and the aerobic bacterium served as a catalyst for the evolution of complex organisms on Earth. And this cooperation continues to this day as mitochondria continue to play a vital role in cellular processes. As a result, all modern eukaryotes, including animals and plants, are carriers of this ancient symbiosis, which has become the basis for their existence. Mitochondria, with their own DNA, continue to remind us of those distant times when life on Earth was just beginning to develop. Chloroplasts, known as solar batteries of cells, originated from ancient photosynthesizing cyanobacteria that were engulfed by ancestral eukaryotic cells. This process of endosymbiosis occurred approximately 1 billion years ago when simple, single-celled organisms began to interact with each other. Cyanobacteria, possessing the ability to photosynthesize, converted sunlight into chemical energy, releasing oxygen as a byproduct. By absorbing these bacteria, eukaryotic cells gained the unique ability to use solar energy directly, which ensured their survival and development in conditions where access to nutrients was limited. This form of symbiosis was mutually beneficial. Cyanobacteria found a protected place to live within the cells, while eukaryotes acquired a source of energy that allowed them to grow and reproduce. Over time, cyanobacteria lost the ability to live independently and transformed into chloroplasts, which still contain their own DNA, reminiscent of the structure of cyanobacteria DNA. This process led to the appearance of algae, the first multicellular organisms capable of photosynthesis, which in turn became the basis for all terrestrial plants. Algae, using solar energy, began to release oxygen into the atmosphere, which fundamentally changed the composition of Earth's atmosphere and opened new ecological niches for other forms of life. An example is the green alga Chlamydomonas reinhardti, which still exists and serves as a model organism for studying photosynthesis. The appearance of chloroplasts marked a significant stage in evolution when solar energy became available to all life on the planet. Every green leaf on a tree or grass blade is essentially a result of this ancient symbiotic process that formed the basis of most ecosystems on Earth. It is important to note that without this event, life on the planet might have developed in a completely different way, and many modern organisms, including humans, might not have been able to exist. Chloroplasts, providing plants with energy, become the main link in food chains, supporting life on the planet. Multicellularity represents one of the most significant stages in the evolution of life on Earth, occurring approximately 600 million years ago. This transition from single cells to complex multicellular organisms can be compared to how humans form societies, creating something greater than the sum of individualities. Initially, single-celled organisms such as bacteria or protozoa existed autonomously and survived, relying on their own functions. However, some of them began to form colonies where cells could interact with each other. These colonies were not true multicellular organisms, but they marked an important step towards further integration. Over time, some of these colonies began to specialize. Some cells became responsible for nutrition, others for protection, and still others for reproduction. This phenomenon is known as cellular differentiation, and it laid the foundation for the formation of tissues. With the passage of time, evolution led from simple colonies to true multicellular organisms where cells not only interacted but completely lost their individuality for the common good. In such an organism, each cell performs a unique function, significantly increasing overall efficiency. For example, specialized cells can more effectively utilize resources such as oxygen and nutrients, which would be impossible in single cells. Furthermore, this organization provides protection from hostile environments. Multicellular organisms can develop complex defense systems, such as the immune system, which protects them from infections and diseases. A crucial aspect of multicellularity is the ability of cells to interact and communicate. Cells exchange chemical signals that help them coordinate their actions. This is much more complex than simple interaction in a colony of single-celled organisms where each cell strives to survive independently. Multicellular organisms, such as plants and animals, developed complex signaling systems that allow cells to work in harmony. For instance, in the human body, approximately 30 trillion cells constantly exchange information, enabling homeostasis and adaptation to changes in the surrounding environment. Moreover, multicellular organisms have a better chance of survival in conditions where resources are limited. Specialization of cells allows for more efficient use of available resources. For example, in plants, root cells absorb water and minerals from the soil, while other cells carry out photosynthesis. This division of labor allows them to survive in conditions where food may be limited. While single cells may be vulnerable to changes in the environment, multicellular organisms, due to their structure, can withstand more severe changes and attacks by predators. Multicellularity also opened the door to the emergence of complex ecosystems where various organisms interact and depend on each other. These interconnections create complex food chains where each element has its place and significance. For example, in tropical forests, plants, animals, and microorganisms form complex interconnections that support the stability of the entire ecosystem. As a result, multicellularity became the basis for the diversity of life on the planet. Approximately 500 million years ago, during the Cambrian explosion, the first true multicellular organisms appeared on Earth, such as trilobites and other invertebrates. These organisms already possessed a complex structure and specialized functions, allowing them to occupy various ecological niches. Multicellularity not only increased the chances of survival for individual organisms, but also contributed to the appearance of a rich diversity of life forms. The Ediacaran biota, which existed approximately from 600 to 500 million years ago, represents a unique group of the first complex multicellular organisms that inhabited the ancient oceans of our planet. These creatures, lacking hard skeletons or rigid body parts, were distinguished by their unusual shape and structure. Many of them resembled discs, feathers, or even mattresses with embroidered patterns, giving the impression that they were made of soft, jelly-like substance. Living on the ocean floor, these organisms led a slow-paced life, absorbing nutrients from water and sediment, which made them dependent on their environment. They lacked active mobility, meaning their existence was largely dependent on currents and other external factors. One of the most well-known representatives of this group is Dickinsonia, which could reach up to 1 meter in length and had a shape resembling a large leaf. Scientists still cannot definitively determine to which type of living organism these creatures belong. Some consider them to be ancestors of modern animals, while others suggest they represent a separate branch of evolution with no connection to contemporary forms of life. Other organisms, such as Charnia, had a structure similar to feathers and could reach up to 2 meters in length, indicating the diversity of shapes and adaptations within the Ediacaran biota. Many of these creatures left imprints on sedimentary rocks which have been found in places like southern Australia and Canada. These imprints, with their strange and unfamiliar forms, create an atmosphere of mystery, and scientists continue to puzzle over how they lived and interacted with their environment. Research suggests that the Ediacaran biota may have been one of the earliest examples of symbiotic relationships, where organisms exchanged nutrients with microorganisms in their surroundings. Such creatures as Tribrachidium had a three-leaf structure resembling a flower or a sliced fruit, and their enigmatic existence continues to raise questions among paleontologists. The Ediacaran biota was nature's first attempt to create complex organisms, and despite their disappearance around 500 million years ago, their traces can still be found in geological layers that have survived to this day. Scientific research conducted using modern technologies such as X-ray tomography and microscopy helps to better understand these ancient forms of life, opening new horizons in the study of their biology and ecology. The Ediacaran biota remains one of the most mysterious chapters in the history of life on Earth. The Cambrian explosion, which occurred around 500 million years ago, was a true revolution in the history of life on Earth. Over a short period of about 20 million years, there was a rapid increase in the diversity of marine organisms, marking the beginning of the appearance of almost all modern animal groups. Oceans, once inhabited by simple life forms, were suddenly filled with complex creatures possessing shells, claws, and jaws. During this period, key groups such as arthropods, mollusks, and chordates emerged, signaling the start of an evolutionary explosion. Scientists like David Erskine studied fossil remains, and their work showed that the diversity of life forms during this time was truly unique. For example, trilobites with complex eyes and hard exoskeletons, which allowed them to hunt and defend themselves from predators, can be found in Cambrian layers. Remarkably, during this period, the first animals with hard body parts, such as the Diploceras, which could reach lengths of up to 1.5 meters and were protected by a sturdy shell, appeared. This moment in the history of life can be compared to an experimental laboratory where evolution played with various forms and strategies of survival. Evidence of this can be seen in the diversity of marine forms, including representatives of the group Kimberlian mollusks, which developed unique mechanisms for feeding and protection. The Cambrian explosion was not only a significant stage in the history of Earth, but also the foundation for the formation of future ecosystems, where complex food chains and interactions between species ensured further development of life. Studies show that during the Cambrian period, there were more than 50 different animal groups on Earth that began to compete for resources. This time became foundational for the formation of ecosystems where predators and their prey began to develop complex relationships. For example, the emergence of the first predators, such as Anomalocaris, caused a real upheaval in food chains. These creatures could reach lengths of up to 1 meter and had powerful jaws, making them formidable hunters. Research using modern technologies, such as computed tomography, allows scientists to better understand the structure and functions of these ancient organisms, opening new horizons in the study of their biology. The Cambrian explosion not only demonstrated the potential of life on Earth, but also became the basis for further evolutionary development, resulting in the appearance of familiar groups such as mammals and birds. It is important to note that during this period, significant changes in ocean geochemistry and atmospheric composition occurred, which could have contributed to such diversity. Specialists like paleontologist Kenneth Farley emphasized that changes in oxygen and carbon dioxide levels in the atmosphere played a key role in this process. As a result of the Cambrian explosion, life on Earth was transformed, bringing new forms, survival strategies, and diversity that became the basis for all subsequent evolution. During this unique period, evolution acted like an artist creating masterpieces, not a mechanical process limited to the survival of the fittest. Burgess Shale, located in Canada, is a true treasure trove of fossils that offers a window into the world of Cambrian life. These shales formed approximately 500 million years ago and represent a unique geological formation where not only the hard parts of organisms but also their soft tissues have been exceptionally well preserved. In such conditions, such as rapid burial in muddy deposits created by turbulent seas, remarkable remains of animals have been discovered, many of which have no modern counterparts. For example, here were found creatures like Anomalocaris, which could reach up to 1 meter in length. This predatory creature with numerous eyes and complex appendages appears to have been one of the first large predators in Earth's history. Additionally, unusual organisms such as Wiwaxia, with its spines and soft body, and Marcopi-like organisms which exhibit strange body forms resembling tubes or plates that do not fit into familiar categories, have also been discovered in the Burgess Shale. Research conducted by scientists such as David Eichel and his team has shown that the Burgess Shale contains more than 6,000 specimens representing around 30 different groups of organisms. This discovery not only expanded our understanding of the diversity of life during the Cambrian period, but also challenged traditional views on evolution. Previously, it was believed that complex organisms began to develop later, but the Burgess Shale provided evidence that complex ecosystems existed much earlier than previously thought. In this context, it is worth mentioning that some of the findings suggest the presence of ancestors of modern animals, such as arthropods and chordates, which fundamentally changes our understanding of evolutionary lineages. The preserved soft tissues, such as muscles and internal organs, provide valuable information about the physiology of these organisms. The chitinous structures found in the shales have become the basis for reconstructing the ecosystems of that time, allowing researchers to understand how these organisms interacted with each other. For example, a study conducted by paleontologist Neil Shubin on a group of fossils demonstrated that some of the organisms used various hunting and defensive strategies, indicating a complex ecology and food chains that existed during that period. Visiting the Burgess Shale allows one to see how the shales are exposed in layers on the slopes of mountains, providing access to this unique historical heritage. In the late 20th century, scientists began to use new technologies such as X-ray tomography for more detailed study of the structure of fossils, which has revealed even more secrets of the Cambrian world. For example, these technologies were used to study the structure of the organism Hallucigenia, which had long remained a mystery to scientists until new data helped to understand its true structure and role in the ecosystem. The Burgess Shale continues to be an active area of research, and each new specimen found in this unique formation can change our understanding of the early stages of life on Earth. Since its discovery in 1935, when paleontologists Richard A. Prang and his colleagues began systematic research on the finds, the Burgess Shale has become a symbol of a revolution in paleontology, opening new horizons in the understanding of the biological history of our planet. The Paleozoic era spans a period from 630 million years ago to 250 million years ago and represents a pivotal stage in Earth's history, during which life on the planet underwent profound transformations. During this time, the foundations of modern biodiversity were established as life ventured beyond the oceans and began to colonize land. At the beginning of the Paleozoic era, the marine environment was the primary habitat for organisms, and it was there that the first steps of evolution took place. Water served not only as a habitat but also as a protective shield against unfavorable conditions, allowing organisms to adapt and develop in a relatively stable environment. However, soon, as a result of geological processes such as plate tectonics, new ecosystems emerged, leading to the appearance of various ecological niches. This process was reinforced by changes in climate and oxygen levels in the atmosphere, creating favorable conditions for the emergence of new species. The increase in oxygen facilitated the development of more complex multicellular organisms, which in turn led to the formation of various marine ecosystems, such as coral reefs, which became homes to numerous species. Evolutionary innovations, such as the appearance of a hard skeleton, allowed marine creatures to be more protected and adapt to various environmental conditions. Gradually, over millions of years, some species began to adapt to life on land, marking a true revolution in the history of life on Earth. This transition from aquatic to terrestrial life was supported by the development of new adaptive strategies, such as the appearance of roots that allowed plants to anchor in the soil and the formation of various respiratory systems in animals, enabling them to survive in an atmosphere with high oxygen content. As a result of this process, by the end of the Paleozoic era, the first forests consisting of tree-like ferns and coniferous plants emerged on land, creating new inhabitants, insects, and the first vertebrates. The Paleozoic era was a time when ecosystems began to exhibit complexity and diversity previously unseen on Earth. During this period, animals and plants began to develop relationships such as symbiosis and predation, making ecosystems more dynamic and resilient. By the end of the Paleozoic era, around 250 million years ago, the Permian extinction occurred, during which more than 90% of all species perished as a result of changes in the atmosphere and oceans. However, this catastrophic period also marked the beginning of a new evolutionary wave, and the numerous species that emerged during the Paleozoic era became the foundation for future biodiversity. The Silurian period, which spanned from 431 to 449 million years ago, was a crucial stage in the history of life on Earth, particularly in the context of land colonization. During this time, the first terrestrial plants, such as mosses and lichens, began to appear on the planet. These primitive organisms, lacking roots and leaves, resembled short green stems rising above the wet soil of coastal zones where salt water met fresh water. These pioneers, unlike their aquatic ancestors, had to adapt to entirely new conditions. Their primary challenge was to protect themselves from drying out. To achieve this, plants developed protective mechanisms such as a waxy cuticle that prevented water loss. These stems, only a few centimeters tall, struggled against gravity using a simple structure that allowed them to remain on the surface. The pioneers of terrestrial flora used spores instead of seeds for reproduction, enabling them to spread even in conditions where water was scarce. The spores of these plants had a hard shell, allowing them to withstand harsh conditions. It is worth noting that the Silurian period was an era of significant diversity among marine organisms, such as trilobites and mollusks, creating a unique interaction between terrestrial and aquatic ecosystems. These early plants laid the foundation for soil formation, which in turn paved the way for more complex forms of life. As a result of land colonization, they created the conditions necessary for the emergence of larger terrestrial organisms in the future. For instance, it was during this time that the first simple terrestrial fungi appeared, which began symbiotic relationships with plants, helping them to absorb nutrients from the soil. This interaction became critically important for the further development of ecosystems. Around 400 million years ago, the first terrestrial mosses appeared on Earth, adapting to new conditions and establishing themselves on land to form primary ecosystems. Against this backdrop, the foundations were laid for future forests and the diversity of flora that would eventually fill the continents in subsequent eras. The Devonian period, which lasted from approximately 413 to 369 million years ago, was truly the age of fish, when ancient oceans teemed with an incredible variety of these creatures. During this time, jawless fish like the mixin and lamprey, which had existed since the early stages of evolution, adapted to life in various water bodies. These primitive fish had smooth bodies and used their suction cups to feed, extracting nutrients from the tissues of other organisms. Simultaneously, armored fish such as acanthodes and stegosaurs, which had protective bony plates, inhabited shallow tropical seas and could grow to significant sizes, sometimes exceeding 2 meters in length. Cartilaginous fish predecessors of modern sharks and rays, began actively hunting their prey, using powerful jaws and sharp teeth to tear flesh. Meanwhile, bony fish, including the earliest ancestors of modern fish, developed various adaptations, such as the swim bladder, which allowed them to control their buoyancy and actively hunt prey in different layers of water. The deep-sea zones of this period were filled with extraordinary creatures, including strange predators that could glow in the dark, attracting their prey. Coral reefs, which began to form during this time, served as homes for numerous marine creatures, including small invertebrates and fish, creating complex ecosystems where each organism played its role. These reef structures provided shelter and hunting grounds, contributing to the development of biological diversity. The Devonian period also saw the appearance of the first fish with jaws, which began actively competing for resources, leading to evolutionary changes and the emergence of new species. The legacy of the Devonian period is preserved in fossil finds, such as fossilized jaws of various species, which have allowed scientists to reconstruct the appearance of these ancient predators. Research shows that during this time, there were already more than 100 different groups of fish, each with its unique adaptations and survival strategies, making the Devonian period a crucial stage in the history of evolution. During the Devonian period, which lasted from approximately 490 million to 360 million years ago, one of the most significant evolutionary transitions occurred on Earth, the appearance of the first tetrapods. One of the most famous transitional creatures of this time was Tiktaalik, which lived around 360 million years ago. This predator combined features of both fish and terrestrial vertebrates. Tiktaalik had gills like a fish, but also developed lungs, allowing it to breathe air. Its fins, up to 30 centimeters long, had a structure resembling primitive limbs, enabling it not only to swim but also to crawl on shallow water. Another representative of this transitional stage was Acanthostega, which existed around 360 million years ago. Acanthostega had 8 limbs, making it unique among early tetrapods. These limbs were less adapted to terrestrial life than those of Tiktaalik, but they already indicated an evolutionary direction. The initial habitat of these creatures included marshy coastal zones and drying up water bodies where they could use their adaptations to survive. In such conditions, the ability to move on land gave them a significant evolutionary advantage. The water in these water bodies often dried up, and only those individuals that could crawl onto land in search of new sources of water or food had a chance of survival. This evolutionary strategy was critically important because it allowed Tiktaalik and Acanthostega to avoid predators by being out of the water. Interestingly, Tiktaalik had not only gills but also a structure resembling ears, indicating its ability to detect sounds in the air. It could grow up to 2.5 meters in length and was powerful enough to hunt other animals. This creature became one of the first examples of adaptation to a new habitat, opening the way for further evolutionary development of terrestrial vertebrates. The structure of Tiktaalik's limbs represented an important step in evolution. Its front fins were already partially transformed into limbs, allowing it to support itself on land. This combination of gills and lungs, fins and limbs created a unique system enabling survival in both water and on land. Studies of fossil remains show that such transitional forms as Tiktaalik were crucial for understanding how animals adapted to new conditions of life and how the transition from aquatic to terrestrial environments occurred. Tiktaalik and Acanthostega were not the only representatives of this group. During the Devonian period, there were also other species that demonstrated various stages of this adaptation. Fossil finds indicate that at this time, not only fish, but also the first terrestrial vertebrates inhabited water bodies, marking the beginning of a new era in the evolution of life on Earth. These creatures became the predecessors of all modern amphibians, reptiles, birds, and mammals, including humans. Carboniferous forests, which existed approximately 300 million years ago, represented an unimaginable world where giant spore-bearing plants dominated. These forests stretched over vast territories, creating dense, humid, and marshy ecosystems that differed from modern forests. In such forests, there were no flowering plants characteristic of our era, which gave them an unusual and alien appearance. Instead, ferns, horsetails, and club mosses prevailed, forming a high green canopy that could reach up to 20 meters in height. The wet climate of the time fostered the development of extensive bogs and small bodies of water, where plant spores could easily reproduce and spread. These forests were home to a multitude of ancient creatures, including various insects and the first amphibians, which sought refuge among the dense vegetation. If we could travel back to this period, we would see a world where light barely pierced the foliage and the air was filled with the scent of decaying plant material. The basis of these forests was not only the giant ferns, but also other spore-bearing plants that filled the space with their green, branching forms. Such a landscape was completely different from modern forests, where flowers and grasses dominate, and the diversity of life includes mammals, birds, and a multitude of insects. In the Carboniferous forests, life followed its own rules. There were no familiar trees, only numerous tall, slender stems reaching for the sky. Due to the absence of flowering plants, the ecosystem was less diverse, but it was full of unique forms of life that adapted to the conditions of their time. These forests laid the foundation for the formation of coal deposits, which later became a vital energy resource for humanity. The formation of coal occurred as a result of the accumulation of organic material that did not decompose due to anaerobic conditions, creating thick layers of peat. Thus, the Carboniferous forests not only left their mark on geological history, but also became the foundation for the future energy balance of the planet. During the Carboniferous period, which lasted from 300 million to 290 million years ago, Earth was home to giant insects that amazed with their size and diversity. For instance, dragonflies of that time had wingspans of up to 70 centimeters, making them the largest flying insects in the planet's history. One of the most famous representatives is Meganeura, which not only had impressive size but was also a predator, hunting smaller insects over ancient swamps. Scientists believe that the high oxygen content in the atmosphere, reaching up to 33%, contributed to this gigantism. This elevated oxygen level allowed insects to develop large sizes, as their tracheal-based respiratory system could effectively supply oxygen even to the largest bodies. Millipedes of the Carboniferous period were also impressive in size, with some individuals exceeding 2 meters in length. These arthropods lived in dark underbrush and were likely predators, hunting smaller invertebrates. One of the representatives is Arthropleura, which, according to paleontologists, could reach lengths of up to 2.5 meters. These creatures had a hard exoskeleton and numerous legs, enabling them to navigate complex terrain, hiding from predators or seeking prey. Giant scorpions like Jacalopterus also inhabited these ancient ecosystems. Jacalopterus could reach lengths of over 2 meters, making it one of the largest known marine arthropods. These creatures hunted in water depths, using their claws to catch prey and moving along the bottom, which allowed them to effectively hunt other marine animals. Spiders like Sauroniops also had impressive sizes, reaching diameters of up to 30 centimeters. These predators spun their webs in dense underbrush and hunted insects using their venom. Their ability to adapt to various conditions made them successful hunters and allowed them to survive in conditions of high competition. Thus, the gigantism of arthropods was a result of unique ecological conditions of the Carboniferous period, where high oxygen content, abundant food, and the absence of large predators created ideal conditions for their existence. These remarkable creatures serve as a striking example of how evolution can respond to specific environmental conditions. For example, during the Carboniferous period, when temperatures were significantly higher than today's and the climate was more humid, insects adapted to life in these conditions, becoming true monsters of their time. Formation of coal seams is a complex and lengthy process that began more than 300 million years ago during the Carbon period, when vast tropical forests covered the Earth. These forests were teeming with diverse plants, including giant ferns, horsetails, and tree-like plants that, upon dying, fell into swamps. In these swampy conditions where oxygen levels were low, plant remains did not decompose completely. Instead, they gradually accumulated, forming thick layers of peat. This process occurred slowly over decades and centuries, as each new layer of vegetation covered the previous one, creating a sort of book of plant remains that was subjected to pressure over time. Over time, peat accumulated under layers of sand and clay and underwent geological changes. Pressure from overlying rocks, as well as increased temperature, led to the transformation of peat into coal. This process is known as coalification. Depending on the conditions, coal can have varying degrees of coalification, from lignite, the lowest quality coal, to anthracite, the highest quality coal, which contains more than 80% carbon. For example, in some regions of the United States, such as the Appalachians, coal seams can reach thicknesses of more than 100 meters, indicating the accumulation of plant material over thousands of years. Modern coal mines can be seen as time machines. When miners extract coal, they are essentially retrieving solar energy that was stored by plants hundreds of millions of years ago. This energy, captured through photosynthesis, accumulated over millions of years and is now used for electricity production, heating, and many other purposes. For instance, coal mined in China provides around 60% of the country's total energy. However, it is important to note that burning coal leads to emissions of carbon dioxide and other pollutants, causing significant environmental problems. In some regions, such as West Virginia, coal mining has a long history. Here, since the 19th century, miners have been extracting coal, contributing to the development of the local economy, but also leading to severe social consequences, including hazardous working conditions and environmental disasters. For example, in 2012, a disaster at the Upper Big Branch mine resulted in the deaths of 29 miners. Such tragedies highlight the risks associated with coal mining and the need to find safer and more sustainable sources of energy. In conclusion, coal is not just a fossil fuel, but a result of a complex geological process that began millions of years ago and continues to this day. This process demonstrates how life on Earth and its changes are interconnected, as well as the importance of understanding the historical context of our energy resources. For instance, in Russia, where coal reserves are vast, coal mines can reach depths of more than 1,000 meters, resulting in unique geological and environmental conditions that differ from those found in other countries. The Permian extinction, which occurred around 250 million years ago, was the greatest mass extinction in Earth's history, during which more than 90% of all marine species and more than 70% of terrestrial vertebrates disappeared. This catastrophic moment in the planet's history can be imagined as an instant when life, having reached an extraordinary diversity, was on the brink of total collapse. At that time, Earth was home to numerous ecosystems where tropical forests, covering vast areas, coexisted with vast oceans teeming with various forms of life. During this critical period, the biosphere encountered intolerable conditions that led to a sharp decline in the number of species. The world ocean, once teeming with fish and invertebrates, suddenly became desolate and devoid of its usual diversity. Flora and fauna on land also found themselves in a dire situation. Forests were dying, and their inhabitants, including dinosaurs and reptiles, were displaced. At that time, silence reigned where life's sounds once echoed. The drama of this moment is difficult to overestimate. Ecosystems lost their fundamental components, and the balance that sustained life on Earth was disrupted. Recovery from this extinction took millions of years, and life returned to Earth only in the form of new species and forms. Research shows that the recovery of ecosystems occurred slowly and painfully, requiring time for adaptation and evolution. During this period, new species replaced the extinct ones, filling the vacant niches and beginning to build new ecosystems. It is worth noting that such events as the Permian extinction serve as a reminder of the fragility of life on Earth and how quickly the surrounding world can change. As a result of this event, the ecosystems that were able to recover differed significantly from the previous ones, which determined the further development of life on the planet. Scientific research shows that it was precisely after the Permian extinction that a new period began, known as the Mesozoic era, which witnessed the flourishing of dinosaurs. An important fact, it was during this period that significant changes in climate and the composition of the atmosphere occurred, which in turn influenced the further evolution of living organisms. Siberian traps represent one of the most colossal volcanic events in Earth's history and may have been a key factor contributing to the Permian extinction. These massive eruptions occurred approximately 300 million years ago and lasted for several million years, covering areas of present-day Siberia with a size of about 2 million square kilometers, comparable to the size of the entire modern Europe. Enormous lava flows issuing from cracks in the Earth's crust formed powerful layers of basaltic rock, reaching heights of more than 1,000 meters. These eruptions were accompanied by the release of vast amounts of carbon dioxide and sulfur compounds into the atmosphere, altering the chemical composition of the atmosphere and leading to a cascade of catastrophic changes. The increase in carbon dioxide concentration could have caused a greenhouse effect, raising global temperatures and leading to extensive climatic changes that disrupted ecosystems. Ocean waters also underwent significant changes. Increased temperature and acidity caused by volcanic activity could have led to the mass extinction of marine organisms such as corals and mollusks. Research conducted by scientists such as Dr. Christopher Field shows that changes in marine ecosystems were so severe that they could have triggered further impacts on terrestrial ecosystems. According to geologists, the activity of the Siberian traps could have been responsible for the extinction of up to 95% of all species on the planet. These colossal eruptions, lasting more than 700,000 years, could not only have destroyed existing ecosystems, but also created new ones that were unable to adapt to changing conditions. Comparison with more recent catastrophes, such as the eruption of the Krakatoa volcano in 1883, demonstrates how even brief volcanic events can have devastating consequences for ecosystems. The Siberian traps, in turn, operated over millions of years, gradually destroying familiar conditions of life and creating an environment in which survival became impossible for many organisms. As a result, this powerful volcanic complex became not only a catastrophe for ancient ecosystems, but also a crucial element in understanding the evolutionary changes that occurred on the planet. The Mesozoic era, spanning the period from 250 to 65 million years ago, is often referred to as the Middle Age of Earth's history, and this is not without reason. It is divided into three periods: Triassic, Jurassic, and Cretaceous, and lies between two major mass extinctions: the Permian, which occurred around 250 million years ago, and the Cretaceous-Paleogene, which ended approximately as 65 million years ago. After the Permian extinction, when about 95% of all species disappeared, Earth began a slow process of recovery. During the Triassic period, which lasted around 30 million years, new ecosystems formed on the planet. Reptiles, such as the ancestors of dinosaurs and the first mammals, which were small and typically nocturnal, appeared. Additionally, the first flowering plants like ginkgo and conifers began to fill the gaps left by the previous catastrophe. The Jurassic period, lasting around 50 million years, was a time of dinosaur dominance, with species reaching impressive sizes, such as the Brachiosaurus, which could reach heights of more than 30 meters. During this period, marine organisms like ammonites and ichthyosaurs thrived in the oceans. Large forests with diverse flora also developed, contributing to the emergence of new life forms. The Cretaceous period, the last of the Mesozoic era, was a peak of evolutionary changes. Not only did dinosaurs evolve, but new groups of mammals and birds also emerged, leading to a significant increase in species diversity. Giant predators like the Tyrannosaurus rex, which could reach lengths of 12 meters and weigh more than 7 tons, and their predecessors like the Spinosaurus, which had a unique body shape and could hunt fish, existed during this time. Simultaneously, new groups of flowering plants arose, dominating ecosystems and replacing more primitive species. The Mesozoic era, often called the Age of Reptiles, was a time not only of dinosaur dominance, but also of great evolutionary innovations in other animal and plant groups. For instance, the first true flowers appeared, significantly impacting pollination and ecosystem development. These changes in Earth's life preceded one of the most significant events in the planet's history, the mass extinction at the end of the Cretaceous period, when more than 75% of all animal and plant species disappeared within a few thousand years. The Triassic period, which began around 250 million years ago and lasted until 200 million years ago, was a time of slow recovery of life after the catastrophic Permian extinction, which wiped out more than 95% of all species on the planet. The world looked desolate. Vast areas were devoid of vegetation, and ecosystems were in chaos. As life began to recover, surviving groups of organisms, such as small mammals and reptiles, started to fill the vacant ecological niches. During this time, new groups of reptiles appeared, including the ancestors of dinosaurs, crocodiles, and turtles. These organisms possessed unique adaptations that allowed them to survive in the hot and arid climate that dominated much of the supercontinent Pangaea. The average temperature on Earth reached 30 degrees Celsius, and frequent droughts forced organisms to find ways to adapt. For instance, some plant species developed deep roots to extract water from underground sources, while others adapted to drier conditions by developing waxy coatings on their leaves. On land, archosaurs, the ancestors of modern crocodiles, preferred wet areas but gradually began to colonize drier territories as well. Notably, it was during this period that the division into two main suborders of reptiles, archosaurs and leptosaurs occurred, which laid the foundation for the further evolution of all modern reptiles. At this time, the first dinosaurs began to develop, and by the end of the Triassic period, they had already started to occupy various ecological niches, from small herbivores to large predators. Fossils found in places like Texas and New Mexico confirm that these early dinosaurs, such as Eoraptor, were only about 1 meter in length, but their diversity already foreshadowed the future dominance of dinosaurs. Throughout the Triassic period, ecosystems gradually recovered, but they remained vulnerable to new changes. For example, at the end of the Triassic period, another mass extinction occurred, which paved the way for further changes in ecosystems, and it was during this time that dinosaurs began to dominate the planet, heralding their greatness in the Jurassic period. The Triassic period was a significant milestone in the history of Earth, when new forms of life emerged from the ruins of the Old World, capable of surviving in the face of harsh competition and climate change. Pangaea was a colossal supercontinent that existed approximately 300 million years ago and united nearly all the land on Earth into a single mass. It formed as a result of the slow collision and merging of smaller continents during the process of continental drift. This landmass, surrounded by the single ocean of Panthalassa, had a climate significantly different from the modern one, as a large part of the planet was located in one place. This meant that the interior regions of Pangaea experienced extreme climatic conditions, including harsh continental effects such as droughts and sharp temperature fluctuations. At the same time, coastal zones had more moderate temperatures, creating diverse ecosystems. Research shows that Pangaea existed during a period when various types of flora and fauna were actively developing on Earth. Its territory was home to vast forests composed of ancient tree ferns and conifers, which later became the basis for future coal deposits. The appearance of dinosaurs is also linked to this supercontinent, as they evolved in conditions where ecosystems were more uniform and interconnected. The formation of Pangaea also influenced oceanic currents. The enormous mass of land changed the direction of water flows, which in turn affected the distribution of heat on the planet. The ocean of Panthalassa, which surrounded Pangaea, was not only vast but also very deep, creating unique conditions for life in the aquatic environment. The existence of such a large land surface could lead to the formation of specific climatic zones different from modern ones, including colder and drier central regions and more humid, tropical zones on its outskirts. Complex interactions between climate and geological processes within Pangaea made it possible to have a diversity of life forms. During this period, Earth was home to many species that later became extinct or evolved to adapt to changing conditions. For example, during long periods of isolation and changes in habitat, many species developed into unique forms that we do not observe today. Approximately at the end of the Mesozoic era, around 180 million years ago, Pangaea began to break apart into separate continents, marking the beginning of a new stage in Earth's history. This process of division not only changed the geography of the planet, but also had a significant impact on the evolution of life, as species became isolated from each other, leading to the emergence of new species through natural selection. The complex dynamics between tectonic plates and climate continue to influence life on Earth today, creating unique ecosystems and conditions for biodiversity. The existence of Pangaea as a single supercontinent significantly determined the atmospheric and oceanic conditions on the planet, which in turn played a crucial role in the evolution of living organisms. For example, changes in ocean currents could lead to the emergence of new climates and biomes, increasing the diversity of life. Internal regions of Pangaea were characterized by harsh and remote territories far from the ocean, with a continental climate featuring extremely hot summers and cold winters. In these vast plains, distant from the sea, temperatures could reach 35 degrees Celsius in the summer months, while winter nights brought temperatures down to -20 degrees. These conditions created ideal conditions for the formation of vast deserts and semi-deserts, stretching over thousands of kilometers. Central areas of the supercontinent were surrounded by high mountains, creating barriers that prevented moist marine winds from reaching the interior, exacerbating the arid climate. On this barren land, rare oases formed around scattered lakes and rivers served as sanctuaries for life, creating unique ecosystems in conditions that would be lethal for most organisms. For instance, the river Thetis, which existed at the time, provided essential moisture, but its course changed frequently due to tectonic plate movements, affecting the availability of water for local flora and fauna. Plants that survived in these conditions developed special adaptations, such as deep roots to tap into underground water sources, or waxy coatings on leaves to minimize evaporation. Animals also faced severe challenges and had to adapt to extreme conditions. For example, some species, like ancient reptiles, evolved the ability to withstand long periods of fasting, while others, such as the ancestors of modern mammals, adapted to nocturnal behavior to avoid daytime heat. These adaptations were critically important for survival in conditions where resources were limited and competition for them was fierce. As a result, these desert ecosystems gave rise to unique biological communities where each living organism played a crucial role in maintaining balance despite the harsh conditions. For instance, some cacti could store water for extended periods, providing food and shelter for insects and small animals, which in turn supported local food chains. These internal regions of Pangaea not only created unique conditions for life, but also had a significant impact on the evolution of species that could adapt to these harsh conditions. The extreme climatic conditions of Pangaea acted as a catalyst for the emergence of new forms of life that later played a crucial role in the biosphere of the planet. The breakup of Pangaea began around 250 million years ago, and was one of the most significant geological events in the history of our planet. Under the influence of tectonic forces, continents began to slowly drift apart, forming narrow maritime straits that later expanded into full-fledged oceans. As a result of this process, the Atlantic Ocean emerged, significantly altering the configuration of the Earth's surface. Initially, the unified supercontinent provided stable climatic conditions and homogeneous ecosystems. However, its disintegration led to the formation of new continental blocks with unique climatic and ecological conditions. For example, the strait that formed between North and South America became a crucial factor in the development of new ocean currents, such as the Gulf Stream, which significantly influences the climate of Western Europe. This new ocean became a vital artery for heat exchange, leading to changes in temperature regimes on land and in water. On the new shore formed by the breakup of Pangaea, diverse biomes began to develop, creating ideal conditions for the evolution and diversification of life. The division of continents led to the isolation of organism populations, facilitating the emergence of new species. For instance, on islands formed as a result of the breakup, such as Madagascar, unique species evolved that are not found anywhere else on the planet. Moreover, changes in ocean currents allowed organisms to migrate over long distances, creating new ecosystems and facilitating interactions between different species. The process of Pangaea's breakup was not rapid. It took tens of millions of years, during which continents slowly moved, allowing scientists to observe changes in the geological structure of the Earth and the distribution of flora and fauna. During this period, new mountain ranges such as the Alps and Himalayas were formed as a result of continental collisions. These changes not only affected life on the planet, but also became the basis for the emergence of various climatic zones, from tropical rainforests to cold tundras. For example, with the formation of new oceans and seas, such as the Indian Ocean, completely new climatic conditions arose, contributing to the development of unique ecosystems in coastal areas. All these processes led to the Earth becoming much more diverse and complex than ever before, providing a platform for endless biodiversity. The breakup of Pangaea served as a catalyst for numerous changes, many of which continue to influence our planet today. These tectonic movements and subsequent changes in the configuration of land and water made climatic conditions more variable and diverse, creating new niches for existing and new species. As a result of this process, which lasted millions of years, we obtained the world in which we live, with its vast array of landscapes and ecosystems. Oceans formed as a result of the breakup now cover more than 70% of the Earth's surface and continue to have a significant impact on the climate and life on the planet. The Jurassic period, which lasted from approximately 230 to 155 million years ago, was an era of dinosaur dominance, when they occupied the leading positions among terrestrial vertebrates. During this time, diverse ecosystems formed on Earth, where dinosaurs, as true titans, filled every available ecological niche. Forests were covered with tall horsetails and ferns, some of which reached heights of up to 20 meters. These moist forests were ideal habitats for various dinosaur species, including herbivores and carnivores such as Triceratops and Allosaurus. Wide plains dotted with cycads and ginkgo trees provided perfect conditions for large sauropods like Brachiosaurus and Diplodocus, which could reach lengths of up to 30 meters. These giants led a nomadic lifestyle, moving across open spaces in search of vegetation. Coastal swamps and lagoons, formed as a result of sea level changes, became homes for numerous marine reptiles, including plesiosaurs and ichthyosaurs, which hunted fish and other marine creatures. At this time, small mammals like prototherians also existed, hiding in the undergrowth to avoid predators. Research indicates that the Jurassic period was characterized not only by a multitude of dinosaur species, but also by a rich biodiversity of other animals and plants, contributing to complex food chains. For example, numerous insects, including mosquitoes and butterflies, played a crucial role in plant pollination. Data on the fauna of the Jurassic period help us understand how these ecosystems functioned and how dinosaurs adapted to various environmental conditions. Today, over 200 dinosaur species have been discovered in various parts of the world, from North America to China, where fossils from this period are found. During the Jurassic period, the planet's climate was warmer and wetter than it is now, facilitating the growth of tropical forests and the formation of shallow seas where thousands of marine organisms lived. The most famous fossil discoveries are from the Lianzhou Formation in China, where dinosaur eggs have been found, confirming their reproduction in these areas. The Jurassic period was a significant milestone in the evolution of life on Earth, and its ecosystems set the stage for future changes that occurred in subsequent geological epochs. Archaeopteryx is an extraordinary creature, about the size of a raven, that served as a classic example of a transitional form between reptiles and birds. This animal, which lived at the end of the Jurassic period around 150 million years ago, combined features of both dinosaurs and modern birds. Archaeopteryx had teeth, a long bony tail, and claws on its wings, indicating its reptilian ancestry. However, its feathers and wings already pointed to an evolutionary transformation that eventually led to the emergence of true birds. This species was discovered in limestone quarries in Germany, with the first finds made in 1859. These fossilized remains became foundational in confirming the theory of evolution, demonstrating how various groups of animals gradually transformed into new forms of life. Archaeopteryx likely lived in the dense forests of the Jurassic period, where it could glide from tree to tree or make short flights using its powerful wings. Its lifestyle was probably active and agile. It foraged in the foliage, hunted insects, and possibly small lizards. The discovery of Archaeopteryx helped scientists understand how changes in animal structure occurred during evolution. For instance, its feathers were not only for flight, but also for thermoregulation or even attracting mates during the breeding season. This species was a crucial link in the chain connecting dinosaurs and modern birds, providing irrefutable evidence that evolution is not a myth, but a real process that has occurred over millions of years. Archaeopteryx continues to fascinate scientists who study its anatomy and behavior to better understand how birds evolved and how they interacted with their environment. For example, the length of its wings was about 20 centimeters, suggesting it could easily maneuver among trees. Research indicates that Archaeopteryx could use its claws to grip branches, allowing it to safely navigate the forest. Thus, Archaeopteryx appears not just as a transitional form, but as a true mystery of nature, continuing to amaze scientists with its unique combination of reptilian and avian characteristics. The Cretaceous period was the final phase of the Mesozoic era, encompassing a time of significant geological and biological changes on the planet. Continents continued to drift apart, and their movement led to the formation of oceans like the Atlantic, which became significantly wider. Sea levels reached record heights, flooding vast areas and creating conditions for the formation of extensive shallow seas. These seas became crucial ecosystems where diverse organisms evolved. On land, there was a true evolutionary revolution. New plant and animal groups filled ecological niches that emerged due to changes in climate and landscape. The appearance of flowering plants was one of the major evolutionary innovations of this time, transforming not only the flora but also the fauna. Flowers attracted insects, facilitating new forms of pollination and seed dispersal. As a result, ecosystems began to take on new characteristics and animals adapted to the changing conditions. This period also saw a diversity of dinosaurs that dominated the land, but they were not the only ones shaping the planet's biosphere. In the waters, giant marine reptiles like plesiosaurs and ichthyosaurs also played a key role in marine ecosystems. The end of the Cretaceous period was marked by one of the most famous mass extinctions in Earth's history, when around 75% of all species, including dinosaurs, disappeared due to catastrophic events likely caused by an asteroid impact and accompanying volcanic activity. This extinction reshaped the planet, paving the way for new groups of organisms such as mammals, which began to flourish in subsequent epochs. The Mesozoic Sea occupied vast areas of modern continents, forming extensive shallow basins that flooded low-lying land areas during high sea levels. During this time, approximately from 130 to 66 million years ago, the Earth's climate was warm and humid, fostering the flourishing of diverse marine life. These seas were true ecosystems, teeming with ammonites, their spiral shells, belemnites resembling modern squids, and marine reptiles such as plesiosaurs and ichthyosaurs, which could grow to significant sizes, sometimes exceeding 10 meters in length. Primitive bony fish also began to thrive in these waters, creating complex food chains. The seabed of these Mesozoic seas was covered with white, chalky mud, formed from the skeletons of microscopic organisms like foraminifera and coccolithophores. These organisms, multiplying in vast numbers, gradually settled on the seabed, forming layers of sediment that eventually turned into chalk, giving the period its name. In some regions, the depth of the sea could reach more than 1,000 meters, providing conditions for biodiversity. The Mesozoic Sea not only provided abundant food for numerous marine inhabitants, but also served as a breeding ground for many species. The water in these seas was warm, promoting the growth and reproduction of algae, which formed the basis for most ecosystems. Evidence of this sea's existence can be found in geological deposits, where fossils reveal the richness of life. Layers of limestone, formed from the remains of marine organisms, are found on many modern continents, including Europe and North America, where they form famous chalk cliffs like the White Cliffs of Dover. These cliffs, rising up to 100 meters above sea level, are not only geological landmarks but also testify to how the Mesozoic Sea once covered extensive territories, creating a unique marine landscape. Today, many of these deposits are used in construction and the production of lime, highlighting their economic importance. Each layer of chalk carries the history of ancient ecosystems that thrived in the warm climate of the Mesozoic era. During the Cretaceous period, which lasted from 130 to 65 million years ago, a significant event occurred in the world of botany: the appearance and rapid spread of flowering plants, or angiosperms. This was a true botanical revolution, as plants with vibrant colors and fruits began to displace the dominant gymnosperms. Studies indicate that around 120 million years ago, the first flowering plants appeared, but it was during the Cretaceous period that they began to rapidly develop and expand their ranges. These plants, thanks to more efficient reproduction mechanisms, particularly symbiosis with pollinating insects such as bees and butterflies, became much more successful in their spread. Unlike gymnosperms, flowering plants offered a variety of forms and structures which contributed to the emergence of new ecological niches. For example, magnolias with their large fragrant flowers attracted numerous pollinators, while planes and figs created dense forests that provided shelter and food for various animals. As a result, Cretaceous forests began to undergo significant changes. They became more diverse and vibrant, filled with green hues and colors that had not previously been present in ecosystems. The appearance of flowering plants also contributed to an increase in oxygen content in the atmosphere, which was crucial for the development of various forms of life, including dinosaurs and mammals. Scientific research, such as the work of paleobotanists, shows that by the end of the Cretaceous period, flowering plants occupied more than half of all terrestrial ecosystems, indicating their dominance and adaptive success. In particular, findings in regions such as North America and Asia show the presence of such genera as Archifructus, which could perform functions similar to both modern flowering plants and more primitive forms of plants. These changes not only altered the appearance of forests but also influenced the evolution of animals, which began to adapt to the new conditions, including the appearance of specialized pollinators. Thus, flowering plants became an integral part of Cretaceous ecosystems, setting the stage for the future forests and fields that we know today. Overall, by the end of the Cretaceous period, the Earth was already home to dense forests filled with flowering trees and shrubs, creating a diversity of life forms that would continue to evolve in subsequent epochs. Around 65 million years ago, one of the most catastrophic events in the history of our planet occurred, the Cretaceous-Paleogene extinction. This event is linked to the impact of the Chicxulub asteroid, which had a diameter of approximately 10 kilometers and struck Earth in the area of the modern Yucatan Peninsula. The impact occurred around 65 million years ago and caused an instantaneous blinding flash that vaporized rocks at the site of collision, forming a crater over 130 kilometers in diameter. The moment of impact was so powerful that it triggered a gigantic tsunami that swept everything in its path, flooding coastal areas. Billions of tons of dust and ash were ejected into the atmosphere, leading to a sharp decrease in sunlight reaching Earth's surface. The consequences of this catastrophic event were devastating. Global fires swept across vast territories, burning forests and vegetation, followed by a sudden cooling known as the nuclear winter. Conditions on the planet changed so drastically that photosynthesis became virtually impossible and food chains collapsed. This extinction affected around 75% of all living species on Earth, including non-avian dinosaurs, which were the dominant group of animals during the Mesozoic era. Studies conducted in the late 20th century, particularly the work of scientists such as David K. Krauss and Neil deGrasse Tyson, confirmed the link between the asteroid impact and the mass extinction. Astronomical data indicate that the collision released energy equivalent to billions of atomic bombs, significantly altering Earth's climate for many years. Experts note that acid rain, caused by sulfur and carbon emissions into the atmosphere, further exacerbated the situation, destroying the remaining flora and fauna. The recovery of natural ecosystems took millions of years, paving the way for new forms of life that ultimately led to the emergence of mammals and, in particular, the appearance of humans. The Chicxulub crater, discovered in the 1990s, has become an important object of study, as its size and structure provide scientists with insights into the consequences of such catastrophic events for the biosphere. The Cenozoic era, which began around 65 million years ago and continues to the present day, is a unique period in Earth's history characterized by significant changes in climate, flora, and fauna. This era of life served as a stage for the recovery of ecosystems following the catastrophic Cretaceous-Paleogene extinction event, during which approximately 75% of all species, including dinosaurs, went extinct. The liberation of ecological niches allowed new groups of organisms to occupy them, leading to rapid diversification of life forms. The Cenozoic era is divided into three main periods: Paleogene, Neogene, and Quaternary, each with its own climatic conditions and biological changes. The Paleogene, lasting from 65 to 23 million years ago, was characterized by a warm and humid climate which facilitated the growth of tropical forests and the spread of flowering plants. This period saw the appearance of the first mammals, small and often resembling modern rodents, which quickly adapted to diverse conditions. The Neogene, beginning around 23 million years ago, brought more pronounced climate fluctuations, leading to the formation of savannas and steppes, where larger mammals, such as the ancestors of modern elephants and horses, began to develop. The Quaternary period, which started around 2.5 million years ago, is marked by sharp climate changes and ice ages, which also contributed to the evolution and adaptation of various species. This era is often referred to as the Age of Mammals, but it is important to note that it was also a time of the flourishing of not only mammals, but also birds, insects, and flowering plants. Birds, for example, began to occupy niches previously held only by dinosaurs, and their diversity significantly increased with the appearance of numerous new species. Insects like bees and butterflies became crucial pollinators of flowering plants, leading to mutually beneficial relationships between them and the plants. Flowering plants, in turn, spread across the planet, creating new ecosystems and supporting the life of numerous animal species. The Cenozoic era also witnessed a significant increase in the number and diversity of mammals, which adapted to various climatic conditions, from tropical regions to Arctic areas. For instance, around 15 million years ago, the ancestors of modern whales returned to the ocean, adapting to aquatic environments. On the other hand, terrestrial mammals began to develop in response to climate changes and habitat conditions, leading to the appearance of species such as mammoths and saber-toothed tigers. A crucial point is that it was during the Cenozoic era that conditions for the emergence of humans were established, who became the dominant species on the planet. Around 2 million years ago, as a result of evolutionary processes, the first representatives of the Homo genus appeared, who began to settle new territories and create tools, marking the beginning of a new epoch in human history. Throughout the entire Cenozoic, Earth underwent significant climatic changes, including temperature fluctuations and sea level changes, which had a profound impact on ecosystems and biodiversity. For example, global warming and cooling led to the formation and melting of ice sheets, directly influencing animal migrations and the flourishing of new biomes. Thus, the Cenozoic era is a dynamic period that encompasses a comprehensive reconstruction of life on Earth, where each change in climate and habitat conditions led to new evolutionary possibilities and the creation of unique ecosystems. One of the striking examples of biosphere changes during the Cenozoic era is the appearance and spread of grasses, which became the basis for many ecosystems, forming food chains and supporting the life of various animals. The Paleocene, which began approximately 65 million years ago, served as a true laboratory for mammals, which, following the mass extinction of dinosaurs, began to fill the ecological niches that had been vacated. During this period, mammals were small, primitive creatures, mostly the size of modern rodents or even smaller. They quickly adapted to diverse environmental conditions, which laid the foundation for their subsequent diversity. Among the early evolutionary experiments of this time were the pantodonts, which appeared around 60 million years ago. These animals had large teeth and could reach the size of modern large dogs. Pantodonts possessed unique features such as long legs and powerful jaws, allowing them to adapt to various ecological conditions, but they did not become a stable group and disappeared around 40 million years ago. Mesonychids, living during the same period, were a group of carnivorous mammals that resembled modern wolves but had long limbs and large teeth designed for tearing flesh. Their evolutionary line proved more successful, and mesonychids became dominant predators, but they too eventually went extinct, giving way to more specialized forms. An interesting example of adaptive radiation is the multituberculates, which inhabited various places and could range in size from rats to elephants. These peculiar creatures had numerous bumps on their teeth, indicating their diverse dietary habits. Their appearance and subsequent disappearance demonstrated how mammals experimented with forms and sizes, but not all experiments were successful. For instance, many of these groups could not survive in the face of climate change and competition with more specialized and efficient forms of life, such as the ancestors of modern mammals. These evolutionary experiments led to the emergence, by the end of the Paleocene, which lasted until 60 million years ago, of more adapted and successful species, such as early primitive primates and other groups that formed the basis for future mammalian diversity. As a result, the Paleocene was a crucial period in which mammals began to establish themselves as the dominant group of animals on Earth, leading to the emergence of new ecosystems and biomes. The formation of the Himalayas began approximately 50 million years ago as a result of a colossal geological process in which the Indian tectonic plate, moving north at a high speed, collided with the Eurasian plate. This collision led to the folding and uplift of the Earth's crust, creating some of the highest mountain ranges on the planet. The Indian plate moving at a speed of around 15 centimeters per year, collided with the Eurasian plate, which was significantly more massive and stationary. This collision, reminiscent of a slow but inexorable dance of two giants, continued for millions of years, resulting in the seabed rising to a height of more than 8 kilometers above sea level. The highest peaks of the Himalayas, such as Everest, reach a height of 8,848 meters, making them the highest in the world. As a result of this geological process, not only magnificent mountain ranges were formed, but also new ecological niches that had a significant impact on the flora and fauna of the region. The Himalayas became a barrier for monsoon rains, altering global weather systems. When moist air from the Indian Ocean collides with the mountains, it rises and cools, leading to the formation of abundant rainfall on the southern slopes, while the northern slopes remain relatively dry. This created unique ecosystems where, in the tropical forests of the south, one can find species like tigers and elephants, while on the higher altitudes, one can encounter snow leopards and yaks. Furthermore, the formation of the Himalayas altered the migration paths of animals and plants, contributing to the emergence of new species. For example, many endemic species, such as the Himalayan blue sheep, have adapted to the harsh conditions of high altitude. Around 30 million years ago, as a result of prolonged erosion and tectonic activity, the Himalayas became a true laboratory for the study of biological evolution, where species adapted to conditions ranging from humid tropics to cold alpine ecosystems. In this context, the Himalayas are not just a geographical detail, but a dynamic system that continues to influence the climate, ecosystems, and biological diversity of the regions adjacent to this mountain range. Today, the Himalayas remain one of the highest and most inaccessible areas on the planet, and their formation continues. The Paleogene climatic optimum was a period when the climate was incredibly warm, and the world felt like a tropical paradise. Subtropical vegetation extended far beyond the current tropics, covering territories now occupied by high latitudes, including the Arctic and Antarctic. Polar ice caps were absent, and instead dense forests teemed with life. This was an era when crocodiles, turtles, and other heat-loving creatures lived carefree in places now covered in frozen wastelands. The diversity of flora and fauna was truly remarkable. On the south, giant mammals like Indricotheres, reaching heights of over 5 meters, roamed, while on the north, in forests, sequoias and eucalyptus trees, which today are found only in Australia, grew. During this time, many groups of animals thrived, including the ancestors of modern mammals and birds, which adapted to warm conditions and evolved rapidly. For instance, in the forests where Canada is now located, ancient mammals like primitive ancestors of elephants and hippos freely roamed vast territories due to the mild climate. Ancient marine ecosystems also flourished. In the oceans, giant marine reptiles and diverse shark species inhabited. This was a time of life's golden age on Earth, when biodiversity reached its peak and many species left behind a rich fossil record. The existence of such warm conditions facilitated the rapid development of ecosystems shaped by tropical winds and abundant rainfall. As a result, landscapes were lush and green, and rivers and lakes teemed with life. Even in regions now cold, such as Greenland, conditions were suitable for forest growth, and heat-loving animals could freely inhabit them. Scientific research conducted in the 20th century showed that during this time, the level of carbon dioxide in the atmosphere was significantly higher than today, contributing to global warming and creating favorable conditions for life. This change in climate led to numerous interesting adaptations in animals and plants. For example, the flora of that time included plants with wide leaves that effectively used sunlight for photosynthesis in high humidity conditions. During this time, the ancestors of modern mammals, such as primates and predators, began to occupy new ecological niches. Paleontologists studying fossil remains found evidence that in these conditions, new species adapted to changes in the environment emerged. The Paleogene climatic optimum was an era when Earth was truly a unique place, filled with life and diversity that we will never see again. This period laid the foundation for further evolution and adaptation of species that, despite subsequent climate changes, managed to survive and adapt to new conditions. Scientific research continues to reveal new facts about how life on Earth changed under the influence of climatic factors and how these changes shaped our planet. In this context, the Paleogene climatic optimum remains a key component in understanding the evolutionary processes that continue to this day. Eocene tropical forests of Antarctica were a remarkable and exotic world that existed around 48 million years ago. At that time, when the continent was located significantly north of its current position, the climate was warm and humid, fostering the growth of lush vegetation. Southern beaches, araucarias, and other species thrived here, reaching impressive sizes. In some areas, the trees could exceed 30 meters in height, creating dense forest masses that served as homes for numerous animal species. Research by paleontologists indicates that these forests were inhabited by marsupial mammals such as ancient kangaroos and Tasmanian devils, which looked quite different from their modern counterparts. Additionally, there were giant flightless birds like the Diplodocus, which could reach heights of up to 3 meters and served as predators in this unique ecosystem. Notably, the fauna was complemented by insects and reptiles, which also adapted to the warm climate, allowing them to survive and thrive. These forests were a true paradise for biological diversity, where each plant and animal played a unique role in maintaining the ecosystem. Despite being located at the southern pole, Antarctica was not only covered in green forests, but also had access to the sea, providing its inhabitants with opportunities for migration and food. However, this world was not eternal. Around 30 million years ago, due to climate change, Antarctica began to sink into an icy realm. The forests disappeared, giving way to lifeless ice sheets that now cover a large part of the continent. Modern Antarctica is a harsh and cold desert, where the average winter temperature can drop to minus 30 degrees Celsius, and the ice cover can reach 3 kilometers in thickness. These climate changes led to the transformation of ecosystems that once flourished in this region, and now only a limited number of adapted species, such as penguins and seals, can be found on the continent. Scientific research on fossil samples found in Antarctica shows that trees similar to those now found in the tropical forests of Australia or South America once grew here. Analysis of the fossils indicates that temperatures in Antarctica during the Eocene could reach 25 degrees Celsius. The process of evolution of cetaceans is one of the most remarkable transformations in the history of mammals. The first ancestors of modern whales, known as Pachycetids, appeared around 45 million years ago and were terrestrial mammals resembling wolves. These creatures hunted in coastal waters and had relatively adapted limbs that allowed them to partially submerge in water. They had long snouts and teeth suitable for catching fish. Fossil remains of Pachycetids indicate that they spent time both on land and in water, suggesting their transitional status. Following them were Ambulocyds, living around 35 million years ago, which were better adapted to a semi-aquatic lifestyle. These crocodile-like creatures had shorter limbs and longer bodies, enabling them to move more effectively in water, although they still went on to land for reproduction and feeding. Fossil finds of Ambulocyds in India and Pakistan show that they had powerful jaws and teeth for hunting fish and other aquatic animals. Gradually, around 30 million years ago, Protocetids emerged, the predecessors of modern whales. These creatures were fully aquatic and could no longer move on land. Their limbs began to transform into flippers, and their nostrils, originally located on the snout, moved to the top of the head, allowing them to breathe at the surface without lifting their head. Fossil finds of Protocetids in Egypt and other regions allow us to trace this process in detail, including changes in the shape of the skull and spine. Modern whales and dolphins, appearing around 20 million years ago, are the final stage of this remarkable evolutionary journey. They possess hidden abilities for echolocation, enabling them to orient themselves in water at great depths. The sizes of modern whales are astonishing. A blue whale can reach a length of up to 30 meters and weigh more than 100 tons, making it the largest animal on the planet. The transformation of terrestrial mammals into marine creatures is the result of millions of years of adaptation and natural selection, as confirmed by numerous fossil finds that allow us to look back into the distant past. The Oligocene cooling began approximately 33 million years ago and was a significant event in Earth's history, altering the planet's climate. This cooling followed the Paleocene climatic optimum, during which warm conditions prevailed, fostering the prosperity of tropical and subtropical ecosystems. The Oligocene period was characterized by a global decrease in temperatures, leading to the contraction of these heat-loving biomes. As a result, areas previously covered by lush tropical forests began to be replaced by more cold-hardy ecosystems, such as deciduous forests of the temperate zone and even tundra in high latitudes. This transition was not merely a change in vegetation cover, but a substantial shift in ecosystem interactions, where new plant species became dominant and many tropical species faced the brink of extinction. Animal evolution also underwent changes. Those unable to adapt to the new conditions went extinct, while others, such as the ancestors of modern mammals, began to develop new adaptations to survive in colder conditions. The Oligocene cooling also affected fauna, causing species migrations in search of more suitable habitats. For example, some primate groups sought refuge in warmer regions, while other species, such as the early ancestors of elephants, began to evolve in the changing climate. This process led to the creation of new ecosystems that formed the basis for modern biodiversity. It is important to note that the Oligocene cooling was a crucial step on the path to the current climate regime of Earth, as it contributed to the formation of conditions that allowed the development of modern flora and fauna. As the climate continued to cool in subsequent epochs, such as the Miocene, new changes in ecosystems occurred, as evidenced by fossil finds that demonstrate how species adapted to changing conditions. This process of ecosystem and biome transformation is fundamental to understanding contemporary climate changes and their impact on living organisms, highlighting the importance of studying such periods in Earth's history. This dynamic led to the emergence of new life forms adapted to cold conditions and created unique ecosystems that continue to exist today. In the Miocene epoch, which spanned a period from 23 to 5 million years ago, there was a significant shift in ecosystems as grasslands began to gradually replace forests. Changes in climate, including global cooling, played a key role in this process. During this time, on the territories of modern savannas, steppes and prairies, extensive grassy landscapes began to form. Particularly in Africa and Eurasia, where the climate became drier and more seasonal, forest areas began to shrink, giving way to open spaces covered in grass. This created new ecological niches, which in turn facilitated evolutionary changes in animals. Hooved animals, such as the ancestors of modern horses and antelopes, developed the ability to run quickly, allowing them to effectively avoid predators on open spaces. For example, the domesticated horse, which appeared only at the end of the Miocene, demonstrates a direct link to the adaptations that occurred in its ancestors during this period. Changes in the dental structure of herbivores also became noticeable. Teeth adapted for chewing. Tough grass became more common. Complex crowns of teeth allowed them to efficiently digest tough vegetation, giving them an advantage in the struggle for survival. Meanwhile, predators adapted to the new conditions, developing sharper claws and improving their speed to successfully hunt the rapidly evolving hoofed animals. These changes in ecosystems also prompted the development of new defense strategies in herbivores. For instance, antelopes began to form herds to increase their chances of survival, as collective actions helped better protect against predators. With the increase in open landscapes and the diversity of species, new forms of life found their place in the changing world, leading to the creation of more complex ecosystems. Thus, the Miocene became an era when grassland ecosystems, due to their unique conditions, played a key role in the evolution of animals and the formation of modern ecosystems. During this time, active migration of various species occurred, contributing to the biological diversity that we observe today. Scientific research confirms that during this period, the formation of the first large herds of herbivores took place, indicating deep changes in the structure of ecosystems. During the Miocene epoch, which spanned from 23 to 5 million years ago, the ancestors of humans, such as Proconsul, Dryopithecus, and Ramapithecus, inhabited the ecosystems of tropical forests in Africa and Eurasia. Proconsul, who lived around 20 million years ago, was one of the earliest hominids, reaching a height of about a meter with a weight of up to 40 kilograms. These creatures possessed a larger brain compared to their ancestors, indicating the development of cognitive abilities. Their direct limbs and more developed shoulder joints allowed them to move through trees using both hands and feet, which laid the foundation for the later evolution of bipedalism in hominids. Life in the food-rich tropical forests enabled proconsuls to be omnivorous, significantly increasing their chances of survival in resource-competitive conditions. Dryopithecus, which appeared around 21 million years ago, was even more adapted to a tree-dwelling lifestyle. Its height reached 1.5 meters, and its teeth showed adaptations to a varied diet, including fruits and leaves. Dryopithecus inhabited dense forests where they actively used their long arms for climbing trees, which allowed them to avoid predators and find food at height. Ramapithecus, who lived approximately from 12 to 8 million years ago, was one of the last common ancestors of hominids. He was able to move both in trees and on the ground, allowing him to inhabit diverse ecosystems. His skull, with a more developed brain, indicated a high level of social organization. During this time in the Miocene, there was a significant divergence in evolutionary lines, leading to the emergence of various hominid species such as orangutans, gorillas, and chimpanzees. These changes laid the foundation for further evolution, ultimately resulting in the appearance of Homo sapiens. The tropical forests in which these ancient primates lived were more extensive than modern ones, and the climate was warmer and more humid, contributing to the diversity of flora and fauna. The Miocene was a turning point in evolution when the ancestors of humans began to develop unique traits that distinguished them from other primates. The Pliocene was a significant geological period of the late Cenozoic era, marking an important stage in Earth's history as the climate and geography began to resemble modern conditions. During this time, continents had already assumed their present positions, leading to the formation of contemporary biomes such as forests, savannas, and steppes. Major climate changes resulted in more pronounced seasons, and temperatures began to fluctuate, creating conditions favorable for the development of various ecosystems. In the Pliocene, more modern groups of animals and plants began to form, many of which we can see today. For instance, the ancestors of modern mammals like horses and rhinos began to occupy their ecological niches, adapting to the changing environmental conditions. Vegetation also underwent significant changes. Forests became more diverse and spread to more northern territories, while savannas began to occupy vast areas. The Pliocene was a transitional period between the warm Miocene and the cold Pleistocene. It ended with the onset of glacial periods when the biosphere was preparing for significant changes. These climate and geographical changes created conditions for the development of new ecological niches and more complex interactions between species. The Pliocene was a time when life on Earth was preparing for the onset of cold periods, which in turn facilitated evolutionary changes necessary for survival in conditions where glaciers began to slowly but surely cover vast territories. The average temperature during this period fluctuated around 32 degrees Celsius, which was significantly different from the temperatures of the Pleistocene, when temperatures began to drop. The Pliocene lasted approximately 3 million years, during which there were significant changes in the distribution of species and their adaptation to new climatic conditions. The formation of contemporary ecosystems in the Pliocene also contributed to the development of migration routes for animals, which became a key factor in their evolution and distribution. As a result of these migrations, many species began to cross the equator and settle in new territories, contributing to their diversification. Existing ecosystems were subject to changes, and new climatic conditions fostered competition between species, which became an important part of their adaptation. The Pliocene laid the foundation for subsequent evolution, and its impact on the biosphere is still felt today. An example of this is the existence of modern mammals, many of which have ancestors that lived during this period. The Pliocene was a time when life on Earth was preparing for significant changes that would occur with the onset of glacial periods. The Messinian crisis of salinity, which occurred approximately 5 million years ago, was one of the most dramatic events in the history of the Mediterranean Sea. At that time, tectonic processes altered the landscape, effectively isolating the sea from the Atlantic Ocean through the Strait of Gibraltar. This led to a sharp decrease in water levels and ultimately to almost complete desiccation of the basin. In the place of the former sea, gigantic salt deposits formed, reaching thicknesses of up to 1,000 meters in some areas. These deposits were the result of regular evaporation of the remaining water, creating unique geological formations that are now visible as salt layers. Over time, rivers such as the Po and others began to cut through the exposed seabed, forming deep canyons and ravines that filled with salt water during rare rainfall events. These canyons, in essence, became temporary riverbeds that transformed the regional landscape, leaving behind powerful erosion traces. In the deepest parts of the basin, salt lakes formed, becoming homes for some unique organisms that adapted to extreme conditions. Changes in the region's climate were no less dramatic. The drying of the sea led to changes in temperature regimes and rainfall patterns, which in turn affected the migration of animals between Africa and Eurasia. At this time, a land bridge formed, allowing various species to freely move between continents, leading to the mixing of flora and fauna as well as evolutionary changes. For example, many mammals, such as the ancestors of modern elephants and rhinos, began to migrate north, enriching the ecosystems of Europe. The restoration of water levels in the Mediterranean Sea, which occurred approximately 5 million years ago, played a crucial role in transforming the entire region. When the strait reopened, the sea was filled with fresh waters from the Atlantic, leading to the formation of new ecosystems and the return of marine life. This restoration became the foundation for future civilizations that would thrive along the shores of this sea. The Messinian crisis was a significant milestone in the geological and biological history, leaving behind numerous mysteries for contemporary scientists studying climate change and species migrations. In the late Miocene, approximately 10 million years ago, volcanic activity led to the formation of the Isthmus of Panama, which became a key element in the alteration of oceanic currents. This narrow land bridge between North and South America not only connected two continents but also divided a single ocean into two large basins, the Pacific and Atlantic. The formation of the isthmus was accompanied by powerful volcanic eruptions and tectonic processes that created mountain ranges and lowlands from ancient oceanic deposits. As a result of this division, there was a fundamental change in the distribution of water masses which affected global climatic conditions. With the formation of the Isthmus of Panama, new oceanic currents emerged, such as the Gulf Stream, which became significantly stronger due to changes in direction and temperature. The Gulf Stream, moving from the equator to the north, brought warm waters to the North Atlantic, contributing to the moderation of the climate in Europe and the eastern coast of the United States. Simultaneously, the increase in the flow of cold waters from the Arctic Ocean into the Atlantic led to the formation of powerful currents, such as the Labrador Current, which intensified temperature contrasts and contributed to changes in climatic patterns in the Northern Hemisphere. These changes in oceanic currents had a significant impact on global climate, leading to cooling in the Northern Hemisphere and gradually contributing to the onset of the Ice Age. Approximately 2 million years ago, the process of glaciation began, with glaciers spreading over northern territories, including Canada and northern parts of Europe. The appearance of ice sheets altered the landscape, creating conditions for the formation of new ecosystems adapted to cold climates. The increase in the area of glaciers, in turn, affected sea level, which fluctuated significantly depending on climatic changes, also impacting marine life. Changes in oceanic currents and climate did not go unnoticed by the biosphere. For example, many marine organisms, such as fish and mollusks, began to migrate to new ecosystems in search of more favorable conditions. As a result of this process, new biological communities emerged, adapted to the changed conditions. These changes weakened the ecosystems that previously existed and contributed to the extinction of some species unable to adapt to the new conditions. The Isthmus of Panama became not only a geographical but also a climatic divider, altering the dynamics of the entire planet. For instance, made possible the formation of stronger seasonal winds, which also affected atmospheric conditions in various regions. Ultimately, the Isthmus of Panama, formed as a result of volcanic activity, radically changed the system of oceanic currents and global climate, leading to significant changes in ecosystems and biological diversity on the planet. During this time, sea level varied from 100 to 120 meters, reflecting the dynamic changes in climate and ecosystems caused by these geological processes. The Great American Interchange was a unique biogeographical event that occurred approximately 3 million years ago when the formation of the Panama Isthmus created a land bridge between North and South America. This bridge served as a connecting link for the fauna of the two continents, which had long developed in isolation, leading to a massive migration of animals. The migration of animals, which began with the appearance of the Panama Isthmus, was not just a casual crossing of borders, but a genuine biological catastrophe. As a result of this exchange, species that were previously unfamiliar began to interact, altering the ecosystems of both Americas. On the northern continent, many species such as moose and bears began to spread south, while on the southern continent, animals like jaguars and capybaras began to move north. This exchange was not only a migration but also a real struggle for survival. Many species were unable to adapt to the new conditions and eventually went extinct, while others, more adaptable, began to dominate in the new ecosystems. For example, some of the species that came from the north were more competitive and began to displace local species in the south. This led to changes in the structure of the ecosystem, where some species became dominant while others became vulnerable. The migration of animals also facilitated the exchange of genetic information, which influenced the evolution of many species. For instance, as a result of this exchange, some species became more resistant to diseases, increasing their chances of survival in changing conditions. Thus, the Great American Interchange became a catalyst for significant changes in biogeography and ecology of both Americas. This process continued for millions of years and had a lasting impact on the formation of modern ecosystems. Today, on the Panama Isthmus, one can see the consequences of this exchange. Many species living in Central America have both northern and southern roots. This process was facilitated not only by natural boundaries, but also by climatic changes that continued to influence the migration paths of animals. All this created a unique mosaic of biological diversity that we observe today. An example of this is the presence of certain species that inhabit only Central America, indicating the significant influence of this exchange on the evolution and adaptation of species. Ultimately, this exchange not only changed the fauna of the continents, but also became an important stage in the evolution of life on Earth, forming unique ecosystems that continue to develop today. The Pleistocene Ice Age, which lasted from 2.5 million to 10,000 years ago, was a time when massive ice sheets up to several kilometers thick covered much of North America, Europe, and northern Asia. These glaciers, stretching from Canada to the central part of today's United States, altered the landscape, creating deep lakes, fjords, and moraine hills. For instance, Lake Michigan, formed as a result of the melting of glaciers, became one of the largest freshwater lakes in the world, with a depth exceeding 200 meters. Glaciers periodically advanced and retreated, changing the relief of entire continents. During their movement, they carved deep valleys and left behind characteristic geological formations such as boulders and gravel deposits. These processes also contributed to the formation of fjords, such as in Norway, where glaciers carved narrow and long sea inlets surrounded by high cliffs. During the maximum glaciation period, sea level dropped, exposing land between continents, creating land bridges like Beringia, which connected Asia and America. This migration of animals and people occurred due to the fluctuations in sea level, allowing new species to move into new areas. Species such as mammoths and woolly rhinos used these bridges to colonize new territories, while people like the Cro-Magnons hunted them, adapting their behavior and lifestyle to the changing conditions of each glacial cycle. Furthermore, with the end of the Pleistocene Ice Age and the beginning of the Holocene, glaciers began to retreat rapidly, freeing up vast territories that became the basis for the formation of modern ecosystems and biomes. This retreat also led to significant changes in climate, allowing vegetation such as forests and steppes to occupy the liberated lands, which in turn influenced the migration and life of animals and people. The glacial periods left a deep mark on the geological history of the Earth, shaping the landscape that we can observe today with its numerous deposits and changes in relief, which testify to the powerful forces of nature. As a result of these changes in landscape formation, unique natural phenomena such as Lake Chad in Africa emerged, which was once part of a vast inland sea and has now significantly decreased in size. Megafauna of the Pleistocene, which inhabited all continents, was an extraordinary world of giant animals that adapted to the harsh conditions of the Ice Age. Mammoths, known for their majesty and distinctive tusks, grew up to 4 meters tall and weighed more than 6 tons. They had long fur and underfur, which helped them survive in cold climates, and their large ears served to regulate temperature. Mammoths formed herds consisting of females and their offspring, protected by an old female who led the group's movements. These mammals fed on grasses, shrubs, and tree bark, allowing them to find food even in the most inaccessible places. Mastodons, which were better adapted to warm climates, differed from mammoths in their smaller size and shorter tusks. They lived in forests and fed on leaves, twigs, and fruits. Their rough and strong fur helped them hide in dense thickets, and their teeth were adapted to grind vegetation. Shaggy rhinos living in Eurasia reached heights of about 2 meters and weighed up to 2 tons. They had long, curved horns, which they used for defense and for finding food in snowy conditions. Additionally, their thick skin protected them from the cold. Giant sloths, such as the Megatherium, weighed up to 400 kilograms and were 4 meters long. These creatures, living in South America, led a semi-dependent lifestyle, climbing trees for rest and food. Their slow metabolism allowed them to go without food for a long time, and they usually fed on leaves and fruits. Saber-toothed cats, such as the Smilodon, were predators reaching lengths of up to 3 meters. Their long canines, up to 25 centimeters long, allowed them to catch large prey, such as mammoths and bison. They hunted in packs, which increased their chances of successful hunting. Cave bears, the largest known bears, weighed up to 1 ton and were omnivorous. They survived in harsh conditions and used caves for shelter and reproduction. Interactions between megafauna species were complex. Some were predators, others were herbivores. and their social structures played a crucial role in their survival. However, most of these remarkable creatures became extinct at the end of the Pleistocene, around 10,000 years ago, likely due to a combination of climate change, reduction of their habitat, and hunting by early humans. For example, in America, species such as the giant sloth and the saber-toothed cat went extinct, which was a significant loss for the ecosystems of the time. The Pleistocene extinction of megafauna is one of the most dramatic events in Earth's history, when a multitude of large terrestrial animals disappeared over a relatively short period, approximately between the 15th and 10th millennia BCE. This event can be compared to nature erasing an entire page from its book, leaving only faint memories of those magnificent creatures that once roamed the planet. During this period of extinction, which affected vast territories from North America to Eurasia, not only the largest mammals but also those species that played a special role in ecosystems disappeared. The selectivity of this extinction is astonishing. While giant mammals such as mammoths, megatherians, and giant sloths became victims of this mass disappearance, smaller mammals, birds, and marine creatures suffered much less. This creates a picture where large forms of life, symbols of power and grandeur, give way to smaller and less noticeable creatures that continue to evolve and adapt to changing conditions. In the process of this extinction, megafauna left behind numerous mysteries and questions that continue to puzzle scientists. Paleontologists like Dr. Stephen Gutenberg study the remains of these creatures, finding their bones and fossils in various places, from glacial layers to caves, to understand how and why these giants disappeared. For example, during the Ice Age, which lasted about 100,000 years, climatic conditions changed, leading to the emergence of new ecosystems that, however, could not support such large animals. The mass extinction of megafauna was a real catastrophe for entire ecosystems in which these animals played a key role. The destruction of megafauna also affected humans, who relied on them as a source of food, resources, and even tools. As a result, this change in the biosphere led to new living conditions and, ultimately, contributed to the development of other species that could occupy the vacated niches. An important aspect of this event is that it occurred against the backdrop of climatic changes that affected the habitat of megafauna. These changes led to a reduction in their range and, as a consequence, to a decrease in population numbers. As a result, the Pleistocene extinction not only altered the appearance of the planet, but also left a deep mark on human history, changing the relationship between people and the world around them. In human memory, only fragments of memories remain of those times when giants roamed the planet, but traces of their existence can still be found in archaeological finds and fossils, which help us understand how the world is structured. Today, scientists continue to study this mysterious and massive extinction, which has left an indelible mark on the history of life on Earth. The extinction of megafauna became not only a catastrophe for nature, but also a lesson for humanity, showing how fragile ecosystems are and how quickly they can change under the influence of various factors. During the Pleistocene megafauna extinction, early humans played a crucial role by hunting large animals with primitive but effective tools. Hunters, armed with spears made from bones and wood, organized into groups, enabling them to systematically eliminate even the largest and most dangerous creatures, such as mammoths and woolly rhinos. These groups acted in coordination, employing hunting tactics that involved encircling and driving animals into traps. Research indicates that as humans spread across new territories, starting from Australia around 45,000 years ago, then through Eurasia, and finally to America, there were so-called waves of extinction. Each new wave of settlement was accompanied by a sharp decline in the local megafauna population. For instance, in Australia, after the arrival of humans, animals like the Megatherium, giant lizards up to 3 meters long, and Diprotodon, the largest known marsupials, disappeared. In Eurasia, where humans began to exploit new hunting grounds, the megafauna, including mammoths and woolly rhinos, faced significant pressure from the new predators. Ultimately, in America, early hunters contributed to the extinction of animals like the giant ground sloth, the size of a car, and the saber-toothed tiger. Scientists emphasize that the combination of hunting, habitat changes through the use of fire for land clearance and pasture creation for wild animals, and the introduction of new predators like dogs, which were domesticated and became human companions, had a disproportionately strong impact on the populations of large animals with low reproductive rates. For example, mammoths, which reproduced once every 4 years, could not quickly replenish their populations in conditions where their numbers were rapidly declining. Studies show that by 10,000 years ago, when humanity had spread across all continents, the megafauna had largely disappeared, leaving only rare species in remote corners of the planet. Modern humans, Homo sapiens, emerged in Africa around 300,000 years ago. Archaeological finds, such as stone tools and fossilized remains, confirm that it was on this continent that the key traits of our species, including complex thinking and communication skills, were developed. Groups of our ancestors, consisting of small family units, began migrating from Central and Eastern Africa, settling in new territories and adapting to diverse conditions. Around 150,000 years ago, they crossed the Red Sea and reached the Arabian Peninsula, then spread across the Middle East and into Europe. These journeys were fraught with difficulties. People traversed deserts, mountain ranges, and straits, encountering variable climates and varied ecosystems. In Europe, Homo sapiens encountered the Neanderthals, an extinct species that inhabited the continent for around 30,000 years. Genetic studies show that there was interbreeding between them, and modern humans inherited some Neanderthal genes, as confirmed by DNA analysis. No less intriguing is the interaction with the Denisovans, another ancient species that lived in Asia. Findings from Denisova Cave in Siberia indicate that Homo sapiens likely had contact with this species, which may have facilitated gene exchange. The unique adaptability and innovativeness of our species played a crucial role in enabling Homo sapiens to settle nearly every corner of the planet. We learned to hunt large animals, gather and process plants, create complex tools, and later engage in agriculture. Around 10,000 years ago in Mesopotamia, agriculture began, leading to the formation of the first settled societies and the rise of civilizations. Adaptation to different climatic conditions was also a key trait of our species. In the cold conditions of Siberia, people learned to build shelters from available materials, use furs for warmth, and start fires for heating. In the tropics, they mastered hunting and gathering methods and used local plants to create medicines. These abilities to cooperate and exchange knowledge between different groups of people facilitated the rapid spread of ideas and technologies, enabling Homo sapiens to survive and thrive in diverse conditions. An example of successful migration is the settlement of Australia, which occurred, according to recent data, around 65,000 years ago, when groups of people crossed the seas in primitive boats. As a result, they adapted to the unique ecosystem of this continent, encountering new flora and fauna. This demonstrates how our ancestors were brave and inventive in their movements. Thus, it is this ability to migrate, adapt, and cooperate that explains why Homo sapiens could adapt to various living conditions and populate all continents. Today, genetic research confirms that there are more than 7 billion people on Earth, all united by a common ancestor who lived in Africa more than 300,000 years ago. The Holocene is a geological epoch that began with the end of the last ice age and spans the time when climate became more stable and warm. This period saw glaciers retreat, revealing new lands suitable for life. Research by geologists and paleoclimatologists shows that sea levels rose, creating the modern coastlines we know today. On Earth, familiar ecosystems began to form. Forests, steppes and savannas, and animals and plants adapted to these new conditions. With the advent of the Holocene, humanity took a decisive step from a nomadic lifestyle to settled living. Archaeological finds indicate that even in the early stages of this epoch, people began to practice agriculture, cultivating crops and domesticating animals. In various regions around the world, the first agricultural societies emerged, adapting wild plants and animals like wheat, barley, and sheep to their needs. These changes led to the accumulation of surplus produce, which became the basis for population growth. The appearance of the first cities was a natural continuation of this process. For example, in Mesopotamia between the Tigris and Euphrates rivers, complex societies with a developed social structure emerged, where some people engaged in agriculture, while others in crafts and trade. Cities like and Uruk became centers of culture and politics, where the first forms of writing and law were born. This period marked the beginning of significant human impact on the environment. The construction of irrigation systems in Mesopotamia, deforestation for expanding agricultural lands, and the domestication of animals led to changes in ecosystems. This also affected the climate. Changes in land use contributed to soil erosion and disruption of the natural balance. The Holocene became an era when humanity, gradually increasing its influence on nature, began to recognize the need for sustainable resource management. For instance, in some areas, early forms of collective management emerged, where communities jointly addressed issues of water and land distribution. This period, filled with new discoveries and changes, laid the foundation for the formation of civilizations that altered the course of history. Humanity transitioned from simple hunter-gatherer societies to complex ones capable of building magnificent temples and advancing science. As a result, the Holocene was the epoch when humanity began actively shaping its living environment, creating conditions for further development. It is important to note that climate change within this epoch also played a role. Stable conditions fostered population growth, which in turn led to the development of new technologies and cultural achievements. Currently, many researchers point out that it was during the Holocene that humanity made crucial steps towards the modern forms of life we observe today, and these changes continue into our time. The Neolithic Revolution, which occurred approximately 10,000 years ago, was one of the most significant turning points in human history. People began to deliberately cultivate plants and domesticate animals, fundamentally altering their way of life. During this period, known as the Neolithic, hunter-gatherers gradually transitioned to a settled lifestyle, choosing locations for settlements near fertile lands. In the Near East, in what is known as the Fertile Crescent, ancient peoples began to cultivate crops such as wheat and barley, laying the foundation for the development of agriculture. These grains provided a stable source of food, enabling people to settle in one place. Around the 13th millennium BCE in this region, the first permanent settlements appeared, such as Çatalhöyük, where archaeologists discovered traces of settled life with developed houses and communal structures. In China at this time, agriculture was also actively developing. Around 7,000 years ago, rice and millet were cultivated, ensuring a surplus for the inhabitants and contributing to population growth. In Mesoamerica, for example, around 5,000 years ago, local peoples began to grow maize, beans, and squash, which became the basis of their diet. These crops not only changed the way people ate, but also laid the foundation for the formation of complex societies. The transition to agriculture led to population growth, which in turn resulted in the complexity of social organization. New roles and professions emerged, such as landowners, craftsmen, and traders. Sedentary life allowed for the development of technologies and the creation of food reserves, ensuring survival during difficult times. Gradually, cities began to emerge, such as Ur and Uruk in Mesopotamia, which became centers of trade and culture. These cities existed thanks to agriculture, which supported large groups of people in one place. Thus, the Neolithic Revolution not only changed the methods of food production, but also led to the formation of new social structures the development of religion and art, and the beginning of civilization's history. Around 5,000 years ago in Mesopotamia, the first city-states began to emerge, such as Sumer, where writing and complex systems of governance developed, which became foundational for the further development of human history. The Holocene climatic optimum, which lasted approximately from 9 to 6,000 years ago, was a period of significant warming on the planet. Average temperatures during this time were several degrees higher than today. This led to substantial changes in climate and ecosystems, particularly in regions such as Northern Africa and Europe. At that time, the Sahara, now known for its arid desert, was covered with lush savannas and lakes. Scientists suggest that during this period, the Sahara was home to a variety of plants, attracting numerous animals and people. Research shows that in the southern Sahara, large lakes existed, such as Lake Chad, which at the time had an area 4 times larger than today. This created ideal conditions for life and facilitated human migration in search of more favorable habitats. In Northern Europe and the Arctic, milder climatic conditions were also observed. Archaeological findings indicate that during this period, fertile lands in Scandinavia allowed for the development of agriculture. This was the time when the first evidence of agriculture appeared in this region, with people beginning to cultivate crops such as barley and wheat. Meanwhile, in Mesopotamia, on the Fertile Crescent, agriculture was already well established. Around 7,000 years ago, the first agricultural communities emerged in this region, where people began to settle and build permanent dwellings. This led to population growth and, consequently, the emergence of early civilizations. With the increase in population, there was a need for more complex systems of management and resource distribution, which in turn led to the appearance of the first city-states. For example, in Sumer, located in modern-day Iraq around 5,000 years ago, writing and accounting systems were developed, which laid the foundation for further progress. This period was also characterized by trade between different regions. A more humid and warm climate facilitated the expansion of agricultural lands, ensuring an abundance of food, allowing people to engage not only in survival but also in cultural development. During this time, changes related to the adoption of agriculture and the establishment of the first settlements were also observed in various parts of the world, such as India and China. Scientists have found that in the Indus Valley around 5,000 years ago, there were complex urban layouts similar to those in Mesopotamia. These facts underscore how climatic changes influenced the development of humanity and contributed to the emergence of the first civilizations. The Holocene climatic optimum was a turning point when people began to consciously manage natural resources, creating the foundations for future cultural and social structures. There is evidence that towards the end of this period, the climate began to gradually change, leading to droughts and cooling, which significantly impacted the further development of civilizations. The Anthropocene is a concept that describes a geological epoch in which the dominant influence on Earth's ecosystems and geological processes is exerted by humans. This is the time when the activities of one species, Homo sapiens, began to compete with the natural forces that shape the planet. For the first time in Earth's history, a conscious being became capable of significantly altering the chemical composition of the atmosphere and oceans, as well as moving vast amounts of rock. Examples of such influence can be seen in the extraction of minerals, deforestation, and large-scale agriculture, which lead to global-scale changes in landscapes. One notable example is the process known as erosion, which is accelerated by human activity. Studies show that in some regions the rate of erosion has increased by 5 to 10 times compared to natural rates. Human influence also affects global biogeochemical cycles. For instance, emissions of carbon dioxide from the burning of fossil fuels and changes in land use have altered the carbon cycle, contributing to global warming. On the other hand, excessive use of fertilizers and pesticides in agriculture has disrupted the nitrogen cycle, leading to issues with water quality and biodiversity. As a result, we are witnessing a mass extinction of species, the rate of which currently exceeds natural rates by 100 times. Humans have become not only users of resources but also active modifiers of their environment. For example, the construction of dams and reservoirs on rivers changes not only local ecosystems but also global climate models. In some cases, such changes lead to the creation of new ecosystems, such as artificial lakes that become homes for new flora and fauna. In this context, the Anthropocene does not merely reflect human influence on nature, but also highlights our responsibility for the state of the environment. Unlike previous epochs where changes occurred due to natural processes, the Anthropocene is characterized by deliberate human activity that leads to profound and often irreversible consequences for the planet. Scientists, such as ecologists and geologists, note that human impact on Earth has become so significant that its effects will be felt in the geological record for millions of years to come. For example, the level of plastic in oceans has reached critical levels, affecting marine life and ecosystems. This new level of interaction between humans and nature requires a rethinking and new approaches to environmental conservation and sustainable development. It is important to understand that the Anthropocene is not just a term, but a reality in which we live, and it demands changes in our behavior and attitude towards the world around us. The time when humans became equal in influence to natural forces marks a new era, not only for humanity, but for the entire planet. The intensity and scale of these changes are underscored by the increasing number of scientific publications on the topics of ecosystem resilience and protection, indicating a growing awareness of the importance of this issue. The Industrial Revolution, which began in the late 18th century in Britain, marked a pivotal moment in human history, when energy stored in coal, oil, and gas over millions of years began to be released over a few centuries. The 18th century was an era when steam engines, developed by inventors like James Watt, significantly increased labor productivity. 80 years later, in the 1830s, factories began to be actively built, using coal to power steam engines. These factories not only revolutionized textile production, but also became magnets for workers, leading to a sharp increase in urban population. By 1830, London had already become the largest city in the world with a population of around 1 million people. The construction of railways in the mid-19th century, such as the line between London and Manchester, opened new horizons for trade and transportation. In the 1830s, the first steamship was launched, which changed not only maritime but also river transportation, allowing goods and people to be transported faster and cheaper. The impact of these technologies on nature was catastrophic. Deforestation for coal and the expansion of agricultural lands to feed the growing population became commonplace. The 18th and 19th centuries were marked not only by economic growth, but also by a sharp increase in resource consumption. The world's population, which was around 1 billion in 1800, increased to more than 7 billion by the 21st century. This growth, in turn, had a colossal impact on natural ecosystems. Air pollution from burning coal, carbon dioxide emissions from cars and factories. In the 1930s, when cars and oil began to be used on a large scale, nature started to suffer from the consequences of this activity, leading to climate change and the destruction of ecosystems. The first studies conducted at the end of the 20th century indicated that humanity had already exceeded the limits of sustainable resource use on the planet. At a time when many countries were actively developing their economies, ignoring the consequences, scientists like James Lovelock began to raise alarms about the possible future of the planet if such a level of consumption continued. The energy that humanity began to extract from fossil fuels not only changed the landscape, but also fundamentally transformed the way people interacted with nature in a way that had not happened for centuries. The 18th and 19th centuries were a time when humans, using accumulated energy reserves, began to significantly influence the climate and ecosystems, which ultimately led to the modern challenges we face today. By 1910, it was estimated that there were already more than 1.5 billion cars on the planet, which daily emitted millions of tons of carbon dioxide, into the atmosphere. Modern climate change, driven by human activity, poses one of the most serious threats to ecosystems and human communities. Since the beginning of the Industrial Revolution in the 18th century, the level of carbon dioxide in the atmosphere has increased by more than 40%, reaching record levels not seen in the last 800,000 years. The primary source of this increase has been the emission of greenhouse gases from the burning of fossil fuels, coal, oil, and natural gas. These gases, including methane and nitrogen oxide, create a kind of greenhouse effect around the Earth, trapping heat and disrupting the planet's natural energy balance. As a result, the average temperature on Earth's surface has risen by about 1 degree Celsius since the end of the 19th century. This seemingly small but critically important temperature increase has led to rapid melting of glaciers, particularly in Greenland and Antarctica, where ice caps lose millions of tons of ice each year. By the end of the 21st century, sea levels are projected to rise by 1 meter, threatening the flooding of coastal cities such as Mumbai and New York, where millions of people could be at risk. Weather systems are becoming increasingly unstable. There are more intense storms, hurricanes, and floods, which are becoming more destructive. According to a report by the World Meteorological Organization for the year 2022, there were 53 tropical storms in one Atlantic hurricane season, which is an exceptionally high number. Heat waves are becoming more frequent and prolonged, especially in Europe and North America, where temperatures in some areas exceed 40 degrees Celsius. This not only threatens human health but also scorches agricultural lands, causing droughts that lead to food shortages. Agricultural systems are beginning to fail as seasonal cycles change. For example, in 2020, Russia experienced an unusually hot summer, which led to an 18% decrease in wheat yields. Climate change also affects ecosystems. The migration of birds and other animals is shifting, leading to imbalances in food chains. Studies show that more than 30% of plant and animal species are at risk of extinction due to climate change. These ecological and social consequences require immediate and decisive action from humanity. Mass extinction in the modern era is a process of species disappearance on Earth at rates significantly exceeding the natural background level of extinction, which is approximately 1 extinction per million species per year. In recent decades, scientists have calculated that the rate of extinction is several hundred times higher than this baseline, creating a worrying picture of lost biodiversity. This mass extinction, often referred to as the sixth, differs from previous ones because its cause is the actions of one species, the human. The main factors driving this process include habitat destruction, environmental pollution, overuse of natural resources, introduction of invasive species, and climate change. Habitat destruction occurs when forests are cleared for agriculture or construction, leading to the loss of habitats for thousands of species. For example, the Amazon rainforest, one of the richest ecosystems on the planet, loses around 7 million hectares of forest each year. Water, air, and soil pollution from industrial waste and plastic materials also have a negative impact on the health of ecosystems. Studies show that more than 90% of marine birds and more than 80% of sea turtles have plastic in their bodies. Overuse of resources, including fishing and hunting, leads to the depletion of animal and fish populations. Thus, in the last 30 years, animal stocks in the oceans have decreased by more than 60%. Invasive species, such as the Norwegian rat, cause the disappearance of local species, disrupting natural food chains. Climate change, caused by greenhouse gas emissions, leads to changes in temperature and sea level, threatening many ecosystems. For example, coral reefs, which support 1,000 species of fish, are suffering from bleaching due to rising water temperatures. Unlike previous mass extinctions, such as the dinosaur extinction that occurred around 60 million years ago due to an asteroid impact, the current extinction is linked to human activity and its impact on the planet. As a result of this process, not only is the diversity of species lost, but also the resources on which human existence depends, leading to catastrophic consequences for future generations. According to scientists' projections, if the rate of extinction does not decrease by the end of the 21st century, half of all species on the planet may disappear, leading to irreversible changes in ecosystems. Coral reefs, known as marine tropical forests, are among the richest and most diverse ecosystems on the planet, but they are currently facing the threat of extinction. These ecosystems support about a quarter of all marine life, including fish, mollusks, and sea turtles. However, according to the World Wildlife Fund, more than 60% of coral reefs have experienced significant bleaching since the end of the 20th century. Bleaching occurs when corals, sensitive to increases in water temperature, lose their symbiotic algae of the genus Zooxanthellae, which provide them with energy through photosynthesis. These algae give corals their vibrant colors, and when corals are stressed, they expel them, turning white and losing their vital functions. Research conducted at the University of Hawaii in the year 2000 confirmed that even a 1 degree Celsius increase in temperature can cause coral bleaching and led to mass colony death. Scientific data shows that between the 90s and the 2000s, there were 3 global bleaching events affecting reefs in the Australian and Caribbean seas. Additionally, oceans absorb excess carbon dioxide from the atmosphere, leading to ocean acidification. This acidification makes it difficult for corals to form calcium carbonate skeletons necessary for their growth and resilience. Estimates suggest that if carbon dioxide levels continue to rise, reefs could completely disappear by the end of the 21st century. Each bleached coral reef structure means not only the loss of beautiful underwater landscapes, but also the disappearance of habitats for thousands of marine organisms that depend on these ecosystems. It is worth noting that coral reefs provide protection from erosion for coastlines and serve as a source of income for millions of people engaged in fishing and tourism. For instance, in the year 2000 it was recorded that coral reefs contribute more than $10 billion annually to the economies of countries in the tropics. The disappearance of reefs would result in economic losses and a deterioration of living conditions for many communities that depend on these ecosystems. Deforestation of tropical forests occurring in recent decades is one of the most destructive ecosystem catastrophes on the planet. Each year, around 10 million hectares of forests are lost, equivalent in size to Iceland. These forests, often referred to as the lungs of the planet, play a crucial role in absorbing carbon dioxide and producing oxygen, serving as home to more than 500 million people and approximately 50% of all known species. The process of deforestation is primarily driven by the creation of agricultural lands, pastures, plantations, mines, and roads. For instance, in Brazil, by the 20th century, it was recorded that around 7 million hectares of Amazonian tropical forests were destroyed for agriculture and livestock. This will lead to a reduction in biodiversity and the loss of unique flora and fauna species such as jaguars, tapirs, and orangutans, which depend on these forests for survival. Deforestation also causes serious soil erosion problems. Forests act as natural filters, holding soil in place, but when trees are cut down, the topsoil begins to wash away in the rain, leading to soil degradation and a decrease in fertility. As a result, lush forests give way to barren areas that are difficult to restore. Additionally, changes in local climate become another serious issue, as trees, by absorbing carbon dioxide, regulate temperature and humidity. Deforestation leads to an increase in temperature and changes in rainfall patterns, which can cause droughts in some regions and floods in others. The water cycle is also disrupted. Trees play a vital role in evaporation and condensation of water, and their destruction can lead to a decrease in groundwater levels and a deterioration in the quality of water in rivers and lakes. The consequences outlined are particularly critical for local communities that depend on forests as sources of food and water. Restoring ecosystems after deforestation often requires decades, if not centuries, putting the future of entire regions at risk. According to a report by the World Bank in 2018, global losses from tropical forest deforestation exceeded $100 billion. The destruction of tropical forests exacerbates the problem of climate change, as each hectare of forest destroyed releases up to 100 tons of carbon dioxide into the atmosphere, further intensifying global warming. Anthropogenic landscapes are defined as territories where human activity significantly alters or completely transforms natural ecosystems. Currently, such landscapes occupy approximately 70% of the Earth's surface, indicating a substantial impact of humans on the planet. These changes occur through various forms of land use, including agriculture, urbanization, infrastructure development, and resource extraction. For instance, agriculture requires vast areas that were once forests and other natural ecosystems. According to the United Nations Food and Agriculture Organization, since the beginning of the 20th century, the area of arable land has increased by more than 30%, leading to the fragmentation of natural habitats. Urbanization, on the other hand, creates new ecosystems where there were once only fields and forests. In the 20th century, the proportion of the world's population living in cities increased from less than 30% to more than 50%, resulting in the creation of megacities such as Tokyo and New York, covering thousands of square kilometers. These anthropogenic landscapes create new ecological conditions that can be both beneficial and detrimental to various species. Some species, like pigeons and rats, easily adapt to city life and find new sources of food and shelter. Meanwhile, other species, such as many insects and birds, face the threat of extinction due to the loss of their natural habitats. As a result of landscape fragmentation, populations become isolated, making reproduction and migration more difficult. Significant changes in ecosystems caused by human activity also affect biodiversity. According to the International Union for Conservation of Nature, more than 1 million species are at risk of extinction, with the primary cause being the destruction of their natural habitats. Studies show that ecosystems altered by humans may be less resilient to climate change and other ecological stresses. These anthropogenic changes present new challenges for nature conservation and require active measures to restore and maintain the remaining natural ecosystems. Restoring such territories often requires significant resources and time, as restoring biodiversity in heavily altered landscapes can take decades. For example, restoring forests after deforestation can take up to 50 years to fully restore the ecosystem. Each year, approximately 13 million hectares of forests disappear, equivalent to an area larger than Greece. These changes not only threaten species but also raise questions about the resilience of ecosystems, which become more vulnerable to diseases and invasions. Urban ecosystems are unique artificial landscapes where asphalt, concrete, and glass interact with nature, creating new ecological conditions. These islands of heat can have temperatures several degrees higher than in surrounding rural areas. For instance, in Los Angeles, the temperature in the city center can reach 37 degrees Celsius in the summer months, while just a few kilometers away in the suburbs, it remains at 32 degrees. Such a temperature contrast leads to changes in the hydrological regime. Rainwater falling on asphalt does not penetrate the soil, but runs into drainage channels, potentially causing floods. The specificity of urban soils also stands out. They often contain high levels of sand and construction waste, making them less fertile, but creating new living conditions. For example, among the plants colonizing cracks in the asphalt, one can find species like sorrel and dandelion, which can survive on poor soils and in conditions of limited water access. Meanwhile, the diversity of fauna in cities is also remarkable. Urban pigeons, sparrows, and rats have adapted to live alongside humans, finding food on landfills and in cafes. Foxes and raccoons have become common inhabitants of large metropolises like New York and Tokyo, where they explore abandoned areas and parks. These animals not only found places to live in urban conditions, but also learned to use the advantages offered by life among people. For example, Raccoons are known for their ability to open trash cans, allowing them to find food in the most unexpected places. Thus, cities become something like laboratories of evolution, where organisms adapt to new conditions at an accelerated pace. Studies show that, for example, the populations of sparrows in London have become smaller over the past decades, which is linked to changes in the urban landscape. Proponents of urban ecology, such as Dr. Jeffrey Kuntz, emphasize that these changes can serve as an example of how species can evolve in response to changes in their habitat, making cities not just places of human residence, but also significant elements of global biodiversity. In essence, the urban ecosystem is a complex and dynamic organism where each species and plant plays a role in maintaining balance. For example, research in Chicago has shown that green spaces like parks and gardens not only improve air quality but also serve as a refuge for hundreds of bird and insect species. It becomes clear that cities can be not only centers of economic activity but also important ecosystems contributing to the preservation of biodiversity. The movement for environmental protection began to gain strength in the mid-20th century as scientists and activists realized that rapid development and industrialization were causing significant damage to ecosystems. In 1962, Rachel Carson published her book Silent Spring, which became a symbol of the environmental movement and brought attention to the dangers of pesticides and toxic substances. The creation of protected areas, such as national parks and reserves, became one of the key aspects of this movement. For example, Yellowstone National Park, established in 1872, was the first national park in the world and serves as a model for the preservation of wild nature. Such parks became sanctuaries for endangered species and ecosystems, providing protection from human impact. By the 21st century, more than 4,000 protected territories had been registered worldwide, occupying about 15% of land and 7% of marine areas. These figures demonstrate that nature conservation has become a priority for many countries. For instance, in the year 2000, the Convention on Biological Diversity was adopted, which aimed to preserve the diversity of life on the planet, and many countries, including Brazil and Kenya, began active efforts to restore degraded landscapes. In Brazil, in 1999, a program was launched to restore the Atlantic forest, which included planting trees and creating corridors between fragmented habitats to ensure the migration of species. In Kenya, the reintroduction of species, such as black rhinos that had disappeared in the wild, was carried out to increase their population and restore the savanna ecosystem. Ecological corridors that connect different fragments of forests and other ecosystems help animals safely move between them, which is critical for the survival of many threatened species. In this context, it is worth mentioning the Wildlife Corridor Project in the United States, which aims to create connecting paths between different protected territories and promotes biological diversity. These efforts demonstrate that humanity is trying to find a balance between development and the preservation of Earth's natural heritage, recognizing that the loss of biodiversity could have catastrophic consequences for future generations. An important aspect of these initiatives is the involvement of local communities in nature conservation processes. For example, in Nepal, community programs for the protection of tigers and rhinos led to an increase in their numbers, which became possible thanks to the active participation of local residents in the management of natural resources. Such examples show that nature conservation is not only the responsibility of governments and organizations, but also the responsibility of each individual. Additionally, the concept of sustainable development, implemented in various international agreements, emphasizes the need to integrate nature conservation into the economic and social policies of countries. The success of wild nature conservation requires a comprehensive approach, including scientific research and practical application of knowledge about natural ecosystems. For example, in 1998, the World Network of Protected Areas was created, which unites the efforts of countries in the conservation of biological diversity and the exchange of experience. This network supports scientific research and provides a platform for discussing best practices in nature conservation. It is important to note that the protection of natural resources and wild nature not only contributes to the protection of ecosystems but also supports the economy through ecotourism. This sector has become an important source of income for many countries where nature and wildlife attract millions of tourists annually. For example, in Costa Rica, ecotourism generates a significant portion of the gross domestic product and contributes to the preservation of forests and the diversity of species. These examples highlight that nature conservation is not only a moral responsibility, but also an economically sound strategy for sustainable development. As a result, all these initiatives aimed at nature conservation and the restoration of ecosystems are becoming increasingly important in the face of global climate change and the instability of ecosystems. According to the UN, more than 1 billion people depend on natural resources for their existence, and the preservation of these resources is becoming vital for their future. Sustainable development is a concept that is based on the idea that current generations should meet their needs without compromising the ability of future generations to meet their own needs. This idea emerged at the end of the 20th century, particularly during the 18th year of the 21st century, when the World Conference on Environment and Development was held in Rio de Janeiro, where the need for a balanced approach to resource use was proclaimed. The principle of sustainable development implies harmonious coexistence between humans and nature, where resources are used at a rate that does not exceed their natural regeneration. For example, if the felling of forests does not exceed their annual growth, they can serve as a source of wood and other resources without harming the ecosystem. This means that if each year only the part of the forest that has regenerated is felled, it is possible to avoid the degradation of fragile habitats and preserve biodiversity. Sustainable development requires that waste produced by human activity should not exceed the ability of nature to process it. For example, in the case of plastic, it is necessary to reduce its use to a level that the ecosystem can safely process, which requires the introduction of recycling technologies and a transition to more environmentally friendly alternatives. It is important to note that sustainable development covers 3 key aspects: economic, social, and environmental. The economic aspect includes the creation of jobs and income growth, which should take into account ecological boundaries. The social aspect implies fair distribution of resources and the creation of sustainable communities, which requires investments in education and healthcare. The environmental aspect focuses on the preservation of natural resources and the protection of ecosystems, which includes not only the preservation of biodiversity, but also the fight against climate change. In practice, this requires the implementation of the principles of a green economy, where economic growth does not lead to the destruction of the environment, but rather contributes to its restoration. For example, the use of renewable energy sources such as solar and wind power plants allows for a reduction in carbon dioxide emissions and minimization of the negative impact on the climate. Another important aspect is sustainable agriculture, which implies the use of methods that allow for the preservation of soil and water, such as crop rotation and organic farming. All these elements should be integrated into a single strategy that allows society to develop without depleting natural resources and without harming the environment. The practical application of these principles requires not only the efforts of governments, but also the active participation of business and civil society. According to the World Bank, the transition to sustainable development can increase economic growth by 1/3 by the 20th year, which underscores the importance of this concept. At the level of individual countries, such as Sweden, successful practices have already been implemented, demonstrating that sustainable development can be not only an ethical choice, but also an economically viable one. The transition to renewable energy sources represents one of the most significant revolutions of our time. Beginning in the late 20th century, this process has gradually encompassed more and more countries seeking to reduce their dependence on fossil fuels. For instance, in 2020, Germany had over 3 million solar panels, allowing the country to generate more than 30% of its electricity from solar sources. Solar panels reflecting sunlight have become an integral part of the landscape on rooftops, in cities, and in rural areas. Tall and elegant wind turbines installed on hills and even at sea create entire wind farms, such as the Hornsea One project in the UK, which in 2020 became the world's largest offshore wind farm with a capacity of 1 gigawatt, enough to power over 1 million homes. Geothermal stations harnessing the Earth's heat are actively developing in Iceland, where nearly 90% of households are heated by geothermal energy, significantly reducing greenhouse gas emissions. Concurrently, the shift to renewable energy sources creates new jobs in sectors such as solar panel installation, wind turbine construction, and energy storage technology development. According to the International Renewable Energy Agency, by 2020 more than 12 million people were employed worldwide in this sector. Meanwhile, the use of these energy sources significantly reduces air and water pollution, as well as CO2 emissions, which is critically important for combating global warming. For example, according to the World Health Organization, transitioning to clean energy sources can prevent up to 7 million premature deaths per year from air pollution caused by burning fossil fuels. Renewable energy not only meets the growing energy needs of humanity but also does so without depleting the planet's resources. Installing solar panels and wind turbines using geothermal sources and hydropower helps maintain the climate balance, which is crucial for future generations. By the end of 2020, it was registered that the share of renewable sources in the global energy balance reached more than 20%, and this figure continues to grow. Restoration of ecosystems, or rewilding, is an active process aimed at returning degraded landscapes to their natural state and functions. These efforts include not only the restoration of flora and fauna, but also the reintroduction of species that play a key role in ecosystems. For instance, abandoned agricultural lands that were once fertile are now often transformed into wastelands where invasive species thrive. Through rewilding, such lands are restored, allowing native plants and animals to reclaim their natural niches. In Sweden in 2012, a forest restoration program was initiated where local tree species were planted after clear-cutting, and measures were taken to remove invasive plants. The forests that are regenerating on the sites of clear-cutting not only increase biodiversity but also improve soil quality, which in turn enhances the hydrological regime. Restored wetlands that were previously drained for agriculture begin to perform their ecosystem functions, including carbon sequestration and water filtration. For example, in the UK, in 2020, as part of a project to restore wetlands in Norfolk, over 100 beavers were reintroduced. These ecosystem engineers create ponds and water bodies, helping to retain water and reduce the risk of flooding. As a result of this process, not only is local flora restored, but new habitats are created for other species. The reintroduction of large herbivores, such as bison or deer, is also crucial for the restoration of grassland ecosystems. For example, in Germany, since 2006, a project to reintroduce the European bison has been successfully implemented. These animals help maintain plant diversity, which in turn attracts predators like wolves returning to ecosystems. Such projects not only increase biodiversity but also help combat climate change through carbon sequestration. For example, forests restored through rewilding can absorb up to 30% of the carbon emitted into the atmosphere. This creates additional opportunities for ecotourism as restored ecosystems become attractive to tourists, bringing income to local communities. In Scotland, where programs for restoring wild landscapes are conducted, the number of tourists has increased by 30% over the past 5 years, directly linked to the active promotion and protection of wild nature. These efforts demonstrate that ecosystem restoration is not just an ecological initiative, but a crucial step towards sustainable development and the conservation of biological diversity. The potential future of Earth appears as a complex network of branching possibilities, where every decision made today can fundamentally alter the trajectory of our planet. For instance, according to the International Institute for Sustainable Development, if humanity takes measures to reduce carbon dioxide emissions by 80% by 2050, this could slow down global warming and keep the average temperature within 2 degrees Celsius of the pre-industrial level. This would mean that ecosystems such as the Amazon rainforest could not only survive but also recover, leading to increased biodiversity and improved living conditions for local communities. Conversely, if current consumption and pollution trends continue, as reported by the World Bank, we may face the loss of up to 30% of all species by 2050, which would result in irreversible changes to ecosystems and lead to ecological catastrophes. It is also important to note that the decision on how to use natural resources depends on political decisions and public opinion. For example, in Norway, the government decided to invest in renewable energy sources, which led to a reduction in dependence on oil and gas, traditionally polluting the environment. This transition creates opportunities for new jobs in the green technologies sector and promotes sustainable development. On other continents, such as Africa, the management of water resources is becoming critically important. It is expected that by 2030 Africa's population will reach more than 1,200,000,000 people, creating enormous pressure on already limited resources. If no measures are taken for rational water use, this could lead to conflicts and further deepening of poverty. There is also the possibility that with the use of new technologies such as vertical farms and hydroponics, humanity could significantly increase food supplies, helping to combat hunger and improve living conditions. However, these technologies require significant investments and political will. Meanwhile, the development of artificial intelligence and automation may lead to a reduction in jobs, creating new social challenges. It is important to understand that we are at a crossroads, and each decision has consequences. An example of this is the environmental protection movement, which, starting in the 70s, became the basis for the creation of international agreements such as the Kyoto Protocol, aimed at reducing greenhouse gas emissions. This process demonstrates how collective actions can lead to significant changes at the global level. In this context, the future of Earth remains open, and every decision made today, whether at the level of individual choice or state policy, can have a decisive impact on how our planet will develop in the coming decades. Every day we face new challenges and opportunities, and it is crucial to consider all aspects of these decisions. In 2020, scientists from the United Nations Global Change Research Institute presented data showing that if ocean pollution is not reduced by 2050, more than 80% of marine species may become vulnerable. These facts emphasize that the future is not predetermined, and each of our decisions today can become the beginning of a new history for the planet. Through millions of years, Earth will continue its geological and evolutionary journey regardless of humanity's fate. The drift of continents will not cease. As a result of tectonic activity, Africa will collide with Europe, leading to the closure of the Mediterranean Sea. This collision is likely to occur approximately 40 million years from now, creating new mountain ranges similar to the Alps, but on an even larger scale. Australia will shift northward, possibly by several centimeters per year, leading to new interactions with other continents and oceans. The Atlantic Ocean will continue to expand, while the Pacific Ocean will contract, potentially resulting in the formation of a new supercontinent. This process is known as the supercontinent cycle, and it has occurred several times in Earth's history, with the last instance resulting in the formation of Pangaea around 200 million years ago. New plant and animal species will evolve, occupying ecological niches left by extinct groups. For example, in conditions of increased temperature and climate change, new tree species adapted to hot and dry conditions, such as the examples we see in Australian eucalyptus, may appear. On other continents, species capable of surviving in conditions of increased salinity, as seen in some desert plants, may emerge. Mammals may evolve in response to changes in habitat, creating new species similar to how modern rodents have adapted to various conditions in different ecosystems. Natural selection will continue, leading to the emergence of new life forms that not only survive, but thrive in the changed conditions. The chemical composition of the atmosphere will also change. An increase in carbon dioxide may lead to the growth of photosynthetic organisms such as algae and cyanobacteria, which will produce oxygen and form new ecosystems. Throughout the planet's existence, climatic conditions have changed, and through millions of years, new glacial and interglacial periods may arise, causing species migration and changes in ecosystems. These changes are inevitable and continue to underscore the continuity of changes that have defined our planet's history over 4.5 billion years. Ultimately, Earth, as a living organism, will continue to evolve, creating new landscapes, ecosystems, and life forms, reflecting the endless process of changes and adaptations. The Sun, our star, will pass through several stages of its existence before it finally exhausts the hydrogen in its core, which will happen in about 5.5 billion years. At this stage, its core will begin to contract under the influence of gravity, while the outer layers will start to expand. As a result, the Sun will become a red giant, its diameter increasing to 90 million miles, allowing it to engulf the nearest planets, including Mercury and possibly Venus. Earth will become uninhabitable long before the Sun reaches its orbit. Already in 2 billion years, the luminosity of our star is expected to increase by 15%, leading to the evaporation of oceans and the destruction of the atmosphere. At the same time, the temperature on the surface of Earth will rise to such levels that our planet will become a scorching desert, similar to the current state of Venus, where temperatures reach around 400 degrees Celsius. This process will be accompanied by an increase in the greenhouse effect, which will finally make Earth uninhabitable as we know it. Ultimately, when the hydrogen reserves are depleted, the Sun will begin to fuse helium, leading to the formation of carbon and oxygen in its core. This process will be accompanied by even greater mass loss, and as a result, the Sun will shed its outer layers, forming a planetary nebula, while in the center, a white dwarf, a hot and compact remnant, will remain, gradually cooling over the course of billions of years. This transformation of the Sun is just a part of the natural cosmic cycle in which stars are born, live, and die. In the astronomical scale of time, stars like the Sun have a finite lifespan, and their evolution affects the surrounding space, enriching it with heavy elements necessary for the formation of new stars and planets. The system we are part of will eventually witness the birth of new stellar systems from the remnants of destroyed stars, emphasizing the endless cycle of life and death in the cosmos. In this context, it is important to remember that every star, including our Sun, goes through its own evolutionary stages, and their fate has significance for everything that exists in our galaxy. The Sun, as a typical star of spectral class G, is one of the millions of billions of stars that populate our Milky Way galaxy, and even after its disappearance, it will leave a trace in the form of new forms of life and matter. Over the course of its history, Earth has experienced numerous catastrophic changes and transformations, from massive volcanic eruptions to ice ages. In the last 450 million years, starting with the Devonian period, our planet has undergone multiple mass extinctions, including the most famous one, the Permian-Triassic extinction event, which saw the disappearance of around 97% of marine species. These events shaped life as we know it today and created conditions for the rise of mammals, which became dominant on Earth's surface. In the last 2 million years, during the Pleistocene epoch, Earth was repeatedly covered in ice, leading to significant changes in ecosystems and facilitating the migration of humans and animals. Humanity, which emerged only about 300,000 years ago, is a unique species capable not only of understanding its past, but also of influencing the future of the planet. We Homo sapiens have witnessed the flourishing of civilizations such as ancient Egypt and Mesopotamia, as well as destructive wars and ecological catastrophes such as the disappearance of the mammoth fauna on Wrangel Island, which occurred around 14,000 years ago. The millions of years of evolution and changes from the formation of continents to the appearance of oceans create an image of Earth as a living system constantly changing under the influence of both internal and external factors. Our ability to conduct scientific research and understand geological processes opens up incredible prospects, allowing us to realize that we are merely a fleeting moment in the context of geological time. This moment is unique because it is in it that we have the opportunity not only to study but also to protect the ecological systems that have evolved over billions of years. We are obliged to preserve this amazing planet, which has become a home to billions of species, including ourselves. Over the past 100 years, humanity has faced serious challenges, such as climate change and the loss of biodiversity, which require us to take responsibility and wisdom in decision-making. Our history, filled with ups and downs, teaches us that every action has consequences, and it is up to us to determine what the future of Earth will be. We must remember that each morning when we wake up on this blue planet, we have the opportunity to choose a path that leads to harmony with nature. It is important to understand that we have a duty to future generations to preserve this wonder of life, which has been developing over billions of years. Each generation has its mission, and it is up to us, the ones living today, to become the guardians of this unique planet. Scientific research shows that in the last 30 years alone, we have lost more than 70% of wild animal populations, highlighting the need for changes in our approach to life. Earth is not just a planet, it is our common home that we must cherish. The night when we close our eyes can become the beginning of an amazing journey through time and space, where we can see how our world has changed, how it has evolved, and how we, humans, have become a part of this great history. Our ability to understand and act can become the key to preserving this planet for future generations and ensuring the prosperity of all forms of life. Knowledge of our long history is not just information, it is our chance for the future. Scientific research shows that there are around 8 million species on Earth, and many of them have not yet been discovered. This inspires further research and discoveries that can change our perception of the world.